Okay. So today we will switch to Chapter 8, Analysis of Oriented Patterns. In the course I give in Calgary, usually I don't come this far, but we have been going a little fast and skipping some details. As I said, if you want to discuss any of those, we can do that separately, or you could read the notes. I put more detail here than needed for a lecture. We have done quite a bit of work on analysis of oriented patterns in our own research work, and for that we went back and read the literature in this area and did some analysis and developed some of our own methods more for analysis of oriented patterns. As we worked on several types of biomedical images, we found that there are such patterns in several images where we could use directional analysis or analysis of oriented patterns or oriented texture. So some of this material is based on our work. Most of the illustrations are from our own work. My own students have done quite a lot of work in this area. So the main point here is many images are composed of piecewise linear objects or curvy linear objects, curvy linear features. They are linear for some distance and then they curve and then the curvature changes, but then there could be another linear portion. So a curved pattern could be made up of a number of linear segments. So it is piecewise linear. And linear or oriented objects possess directional coherence or correlation. They are coherent in some sense of some property, or the values are correlated in that direction, not in all directions. And that can be quantified and examined to study the underlying pattern or texture. Sometimes we may not want to call it texture. Texture has some very specific connotation. So here, when you have these ligament patterns or fibroglandular tissue, is that texture like what we would mean in terms of something printed like that shirt or some of your dresses? That is a different kind of texture. This is not so clearly texture, so that's why Rao in his book has called this weakly oriented structures or weakly structured texture. So in texture segmentation, which is a fairly large topic in the literature, a common approach that's been used to identify differing regions is to find the dominant orientation of the texture elements. And directional analysis is useful in not only the identification of oriented patterns, but also image segmentation and characterization of oriented or weakly ordered texture. So let's look at some oriented patterns in images. In many cases of natural materials and also artificial man-made materials like clothing or ropes and threads and so on, strength is derived from highly coherent or organized or oriented fibers. When you take a rope, there is an ordered pattern of the fibers in the rope. If you take a small section, you have parallel lines, but then overall there is some braiding. A normal healthy ligament is composed of bundles of collagen fibers. I showed some pictures earlier and you will see more of them, that are coherently oriented along the long axis of the ligament. The ligament is only this long, but we are talking about fibers that are a few tenths of nanometers in diameter. An injured or healing ligament, on the other hand, contains scabs of scar material that are not aligned. They are collagen fibers, all right, they are deposited in the healing process, but they don't have that orientation, and the preferred orientation develops slowly over time. I'll show that. So the determination of the relative disorder or order, is there order present or is it disorder? And you need to characterize that. Of collagen fibrils or fibers could provide an indicator of the health, strength, and what is called functional integrity. Can this function and bear the load of normal activity or sport activity if one is engaged in football or soccer or hockey and so on. So a few examples: fibers in muscles and ligaments, fibroglandular tissues, ligaments, vessels and ducts in the breast, and vascular networks in ligaments, lungs and the heart, and bronchial trees in the lungs. There are a number of figures in the notes that you can refer to later on, and we have gone through some of them. So in man-made materials such as paper and textiles, again, strength or just the object like paper. In paper, you're not looking for strength. You don't want it to rip easily, but still, it's not strength, but the very existence of that sheet of paper depends upon individual fibers that are somehow put together in some order. The strength of the material is related to the organization, not necessarily always parallel, but there is some organization, and that constitutes that material. So information related to orientation has been used in remote sensing to analyze satellite maps or aerial photogrammetry for the detection of anomalies or even structures, man-made patterns and natural patterns like rivers, buildings, and farm land and so on. So because man-made structures tend to have strong linear segments, then directional features can help in the identification of these structures. So how do you measure this? How do you characterize directional distribution? We know that when you measure a gradient, like using the Sobel operator, if you just take one of them, you get the x derivative, the other gives the y derivative, put them together as the derivative of x plus j times derivative of y. You get a complex quantity. Magnitude gives just the magnitude, but the angle gives you the arctan of the ratio of the imaginary part to the real part, gives you the orientation or direction of the gradient. So how do you characterize a distribution of that? Typically against angle, magnitude is separate. Statistical measures used in the rectangular coordinate system may not be suitable. So we need to switch to polar coordinates or some angle-based coordinate system. And another question arises, do you want to go 0 to 360 or 0 to 180? In most cases, 0 to 180 will be suitable because a line going like that could be oriented that way or this way, it doesn't matter. So we could limit our analysis to half the circle, 0 to 180, or if you prefer, plus minus 90 degrees above the horizontal, depending on the application. The Rose diagram is a graphical representation of angular distribution of something, of directional data. So corresponding to each angular interval of bin, there is a sector or a petal of the rose. It's not a rose, but it's called a rose diagram, and it is plotted with that either the length of that petal or the area of the petal being proportional to the data in that angular band. So the radius could be made proportional to the area of the image components, or the area of each sector could be made proportional to the square of the directional data, depending on what you want to represent and how you want the plot, the Rose diagram, to look like. You could also compute what is known as the principal axis. So I have this object, and if it is vertical, then there is a principal axis like that. Or if it is like this, the principal axis is that way. So the orientation could be orientation of an irregular object, could be formulated or identified by taking moments and finding the principal axis. So the moment of inertia, or the moment as we saw earlier, of fxy, but now with respect to an angle, theta. So m theta, integral over all space, x minus x bar, the centroid, sine theta, y minus y bar, cos theta square, fxy dx. So this is moment of inertia about that line, which is passing through the centroid and at that angle theta. And if the object has preferred orientation, then there will be a large moment at that angle. If it is a perfectly circular or spherical object, there is no preferred orientation. A ball has no preferred orientation, whereas an ellipse has, this thing has a preferred orientation. There is an axis. Of course, you can say there is a long axis and a short axis, and you will take the long axis as the orientation. So, to make m theta independent of the choice of coordinates, then you could let x bar, y bar be 0, and then you get this equation, and go through that, expand the square, and you get the second moment is 2, 0, 1, 1, and 0, 2. And MPQ is the pqth order of the moment, as we have seen before. So you go ahead and solve that, you get tan 2 theta is 2m11 over m20 minus m02. So by computing these moments and solving for this equation, we can find the slope or direction of the principal axis of this object, which is, the principal axis would be like that. Now, an image might not have simply one object with one orientation. There could be multiple objects. Then what you do? Then you get some average measure. If there are many of these objects present in the image at multiple angles, then it is hard to say what is the orientation of the image. Then you may want to detect each one of these and get the orientation distribution of all of these objects in the image. To do one such axis for the entire image may not be meaningful. So the previous discussion assumed there is one object in the image. But if you have 50 of them, then if they're all aligned in the same direction, fine. But if they have different orientations, then you get some average value. So if there are a number of directional components at different angles, then theta will represent their weighted average direction. It cannot detect the existence of components in various angle bands, so this is not very useful in practice. You could take angular moments of an angular distribution. You can get angular distributions of some representation of the image. For example, the Fourier transform. We saw the Fourier transform for a rectangle has its, or a line has its components concentrated along a line that is perpendicular to the orientation of the line in the image domain. So if you convert the Fourier transform into the polar coordinate system and get a function of r theta, at some angle there will be a large concentration of energy. So you can plot the concentration of energy, or just the energy of the power spectral energy or power of the image. In signal processing, power and energy are related by the time. Power is energy divided by time. In images, there is no time. So, do you want to call it power spectral density or energy spectral density? That distinction is not made. So, sometimes I may mix energy and power. Here, they are the same. One could be normalized if you wish, but that doesn't matter. We are only looking at the distribution. So, suppose somehow you got this distribution, Pn. Pn is the normalized weight or probability for the nth angular band. 0 to 180 degrees, you may break into 10 bands of 18 degrees each, or 18 bands of 10 degrees each, how many ever bands you want. And theta n is the center of the nth angle band in degrees or radians, as you wish, and take the moment. N is the number of angle bands. That is a moment of the angular PDF, angular probability density function, or distribution function of some kind. You will see examples of this as we go through this chapter. And then, in most cases, you would want the principal axis, so take the average. That will give you the main axis of concentration of energy in that probability density function if it has been normalized. You are also interested in the dispersion. Is it concentrated only in one angle, or is there some spread around that angle, or is it spread all over? For that, you take a variance in angle, theta n minus theta bar square times Pn. These are all the same as the probability density function moments that we saw earlier. But now the interpretation is slightly different in that this is an angle and this is the probability or proportion of some measure occurring in that angle band. Okay? Now when you have two distributions, P1 containing P11, P12, P1n, then you can see this as a vector also. It's in the discrete representation, it is simply a series of values. So it's a vector. You can compare one vector with another using distance measures, Euclidean distance or any other distance you like. So you may treat the Rose diagram or the angular distribution of whatever it is you're measuring, get the moments, treating it as a PDF, but you can also treat it simply as a vector. I computed 18 values with angle band of 10 degrees, 0 to 180. I computed the energy or something. So I have a vector with that dimension for this image and that image and so on. I won't compare the images. You compare these vectors and take some distance between them. So you can take the distance P1 with reference to P0 as this Euclidean distance. Or the Manhattan distance is just taking the absolute value of the difference instead of squaring. So you're comparing vectors derived from the images now. But the vectors are made up of the angular distribution. Okay? Now this could be some standard reference, or it could be P1 minus P2, one image comparing with another image. You can take entropy like we have seen before, Pn log Pn. If it is uniformly distributed, it has no preferred orientation, it is isotropic, then the entropy is maximal. If energy is concentrated in only one angle band, there is preferred orientation, then entropy is small or minimum if it is only exactly one band. So the entropy is not giving the angle band of primary orientation or the principal axis, but it gives you the spread, similar to variance that we saw. Variance is also a spread. Entropy is also a measure of spread of the distribution. All right? Any questions about this? Okay, so how do you get directional components out from a given image? We have seen the Fourier transform of an oriented linear segment is a sinc function. If it is a straight line, it's a sinc function only at that orientation, at the corresponding orientation in the frequency domain or along the corresponding axis. But if it has a certain thickness, then there is another sinc function in the orthogonal direction. Two sinc functions multiplied. So based upon this property, we can say we can select components at a certain angle. Now displacement, if there are several lines at multiple displacements for the same angle, they will all add up and the Fourier transform will have energy in the same angle band, all of them combined in the same angle band. If you take the magnitude spectrum, phase is different. So the magnitude spectrum will remove the effect of displacement, and all straight lines of the same orientation will have energy in the same angle band. If the angle changes, the orientation in the frequency domain changes. So we can select linear component specific angles by putting a filter extracting Fourier domain components in a particular angle band. If you put an ideal filter, we get ringing artifacts. We saw that. So the filter has to be shaped appropriately to have smooth transition from the pass band to the stop band. So here are two line segments. This is on a discrete grid, a digital image, and it's been cut. So when you cut an image like that, it's like putting a window. And putting a window means multiplying this line, which perhaps is going plus minus infinity, but we put a window, so that means multiplying that line with a rectangle function or a square function. So the Fourier transforms of the two will be convolved. The Fourier transform of the line is a sinc function, all right, but it is convolved, Fourier transform of that line will be a 1D sinc function in that orientation, but the Fourier transform of the square window or rectangular window you put is a 2D sinc function. The two are convolved and there is spread in the other direction. Or if the line has thickness, the same thing happens. So the Fourier transform of a line that is in a finite space digital image or discretized image will have some other artifacts. But still, you can see that most of the energy is here, and if you take only that part, it represents this line. If you rotate it, then there is a corresponding rotation. Note that the energy in the frequency domain, this axis is perpendicular to the orientation of the line in the image domain. There are some studies on the human visual system that have shown that we have orientation selective structures. Whether they are Gabor filter-like filters, bandpass filters, it's not clear. Some have suggested that. So Marr showed that the orientation of linear segments, primarily edges, is important in forming a primal sketch. So when you see something with high contrast, black pattern on white, and then you close your eyes, you will have a pattern of the edges only. And sometimes you may be able to see multi-scale versions of that. So stare at something like that black frame for a number of seconds, and then close your eyes, you will see the inverse of that, because we are doing some edge detection. And there are some other artifacts also. Color, there could be some reversal of colors. If you refer to my color image processing book, and if there is time, I'll include a seminar on color image processing at the end. So Marr called it the primal sketch. All of that information is sent. So it is not just the picture, the intensity information that is sent from the retina to the visual cortex in our brain, but some other processed versions in between. There are some filters, and there is some neural encoding and data compression, and that information goes to the visual cortex. That's been suggested by a number of researchers. So other researchers have used oriented bandpass filters to simulate the human visual system. What are oriented bandpass filters? Gabor filters, which we will see in detail later on. Subhashish Chowdhury, who did his MSc with me, and later on he came back and he was the director of IIT Mumbai, he used a set of bandpass filters to obtain directional components in electron microscopy images of ligaments. I'll show you that. And one of my colleagues, Dr. Bruton, designed high-quality fan filters. Fan meaning an angle-specific, a filter with a passband that is a sector in the Fourier domain. I'll show you that. So let's look at sector filtering in the Fourier domain. So let's look at a line segment of some orientation A and y-axis intercept B in the xy plane with some limits plus minus x plus minus y. The equation is y equal to ax plus b, and let x be equal to y, so it's a square image. This is just the formulation of the image like what I showed you. So fxy is equal to 1 along the the line, y equal to x plus b. So let x be y minus b over a, then the Fourier transform comes out in this manner with a sinc function. The exponential factor depends upon the placement of the line. There is a phase shift depending on your origin. So this is just a phase factor. This is some scale factor depending upon these parameters of the line. But we are more interested in this sinc function, u over a plus v. So there is a relative scale factor of a between the two frequency axes. That shows the preferred orientation. So the Fourier transform of the line is a sinc function with an argument that is a linear combination of the two frequency variables with a slope that is a negative reciprocal of the slope of the original line, which is this 1 over a. So it is not symmetric anymore because a line is oblong, not a square. It's a very thin rectangle. The intercept is translated to a phase shift b over a in the u variable. The sinc function is oriented at 90 degrees to the original line, centered about the origin, regardless of the intercept of the original line. Like this. Doesn't matter where the line is placed. If I push this there, you get the same thing. If I displace the line, you get the same thing in magnitude. The phase factor is not displayed. If I rotate the line, this also rotates. So this allows us to form filters and say, I want only components in this angle band. Of course, you must have conjugate symmetry. You have to pass the negative frequencies also. So spatial components in a certain angle band may be obtained by applying a bandpass filter in an angle band perpendicular to the band of interest and then applying the inverse transform. What should be the shape of that filter? We will see later. A spatial offset of the lines would only result in a phase shift. The magnitude remains the same. And filtering typically is done in magnitude only. You let the phase be the same as in the original image. So this is a fan filter in the frequency domain. This is the horizontal U axis. This is the vertical V axis. DC is here. This is called a fan, like the blades of a fan when it's not running. So there is symmetry. Positive U, a positive V frequency, negative V frequency, positive U frequency, negative U frequency. Okay? Symmetry in both U and V, not isotropy. I'll skip some of this review. The problem with the Fourier domain technique is filters don't behave well with occluded components. If there are two lines like this, what is the orientation at the intersection? There is no orientation there. You need a certain length in order to define orientation. And if there are multiple occlusions, one line superimposed on others, then there is a bit of a confusion in filtering and you may not get good results. Again, it depends on the filters you use. Smearing of line segments occurs, and that leads to inaccurate results when inverse transformed, and typically you would apply a threshold later to detect only the lines. And we have such problems. There is truncation artifacts and spectral leakage because the bandpass filter will be removing a number of components and there is some transition. It cannot go like that forever. Gabor filters do, but at some point you have to cut it off, and when you cut the filter, there will be ringing in the inverse transformed image. There will be truncation artifacts and spectral leakage when the linear segments are truncated in the image domain. The spectral components are smeared. When an image is truncated with a window, the Fourier transform of that object, which we assume is much bigger than that window, will be multiplied by the Fourier transform of that window, which typically is a square or a rectangle, which has a 2D sinc function as the spectrum. So the spectrum of the original line or pattern is convolved with the spectrum of the window, which is a sinc function, and that sinc function will just mess up the spectrum through convolution. The same thing happens in 1D. When you truncate a signal, the spectrum is not the real spectrum anymore. And truncation may not be by applying a window, it is just that we start observing here and stop observing there. Signal has been going on. So just that is a window, an implicit window. So there are these artifacts. So Chowdhury designed a filter to minimize such artifacts. We broke the spectral domain into 12 bands of 15 degrees each, and we made a combination of the fan filter, like you saw before, but the fan filter is ideal. You want to make that transition smooth. So we put a cosine function in the angle. But the cosine function also ends there. There is a certain bandwidth given to it. Theta minus theta naught is the center of the band, and it is smooth up to a certain distance, or certain angular separation. And then this is a Butterworth bandpass filter. There is a low frequency cutoff and there is a high frequency cutoff. We saw the Butterworth filter earlier. Here we're using just the frequency f. We're taking a ratio, so it doesn't matter whether it is omega or f, but in image processing, the 2 pi factor will be cancelled out anyway. So there is a low pass filter and a high pass filter, and that combined will give you a band pass filter. And then there is a ramp here. It's a ramp with 1 minus beta FR. FR is the radial frequency. So it reduces. So it's suppressing some high frequency components. We have a low pass filter, but still we are putting another filter on top of that. So it's a combination of an ideal fan filter, which is defined in angle there, but with a raised cosine window weighting. It's a Butterworth bandpass filter with a low pass and a high pass component, and a ramp shaped low pass filter, which is this. So there are all these parameters that we had to specify in order to get this filter. You don't need to worry about all these specifications. For a certain application, these are the parameters we used, and the filter looks like this. So this is the bandwidth of the fan filter. The gain reduces as we go to higher frequencies. The gain reduces as you go away in angle from the center of this angle band, and the gain also reduces as you come towards DC. There is a high pass filter. There are 2 low pass filters, the ramp and the Butterworth, and the cosine weighting makes it smooth. Now, oddly enough, at that time when we designed this in 1985 or 86, we were not aware of Gabor filters. Gabor filters in 1D had been published in 1940s, but in 2D, the important papers in Gabor filters came a little later or around the same time, and we had missed that. I need to check whether it came later or at the same time. So we designed our own combination to make this filter as smooth as possible. Later on, we switched to Gabor filters. If we had known Gabor filters at that time, we would have used them. So this gives you 12 angular component images. One forward Fourier transform of the given image, 12 filters are applied, and 12 inverse Fourier transforms have to be computed. At that time, that was a lot of work for the wax computer we had. And the university was getting supercomputers, first array processors, and then parallel processors. So Subhash has spent a lot of time learning. I also went and took those classes to write programs for array processors in supercomputing. And then later on, we parallelized some of the algorithms when the supercomputer switched to parallel machines. Now, it doesn't matter. Speed of these things doesn't matter. Ordinary computers can handle this fairly easily. And the pictures were not that big. They were 400 or 500 pixels on each side. So each component contains the linear components of the original image in the corresponding angle band, corresponding meaning perpendicular. There will be some artifacts, so you need to threshold, and Otsu's thresholding method, which is very popular. I mentioned Otsu's paper has a high number of citations, although it is a short communication article in one of the IEEE transactions. Do you want me to go through Otsu's method? No. Otsu's method is a thresholding method, and the details are here. I'll skip that. It gives you an optimal threshold based on some measures of variance and mean of the distributions, mostly variance. The mean also comes in, and some prior probabilities. So I'll skip all of that. So here we have a test pattern we made up. In all of our works, we have used test patterns that we make up so we understand what is happening. What will happen with some image where we know we have multiple directional components of different thickness, thick and thin, and different orientations and substantial masking or overlapping. These lines at 135 degrees are overlapped by all of these. So detection of those is difficult. So this is the Fourier transform. The vertical lines are here. There are thick vertical lines, so there is a spread. The horizontal lines will be there. The 45-degree lines will be here, and the 135-degree lines will be there. All of them, regardless of position. So if you extract the 135-degree components in the frequency domain, this is what we get, the 45-degree components. Now there is overlap. Note that there is substantial overlap for these. But still we are getting this. The overlap is more here, so there is a bit of a confusion there. You apply a threshold, we get fairly good results. Not perfect. We computed the error between this and the design straight lines, and we computed some error measures. In my lectures and seminars, I don't go through all of those error measures. They are for the sake of publication. You give that. They're in the book in the notes, but I don't read all of that. Not necessary. But you need to quantify what is the error, measure it, and show, analyze. So the vertical band, we get this. For the 135 degree, we lost some. There is substantial overlap. You can't even see there. The contrast of these lines is poor. So that happens. So the error is high for this band. For the others, the error is not so bad. Dr. Bruton and his colleague, they designed fan filters as digital filters. I won't go through all of the details here, but the transfer function in the S domain, Laplace variable, is defined as a ratio of two polynomials where PQ are the coefficients and S1, S2 are the Laplace domain variables in the two directions, horizontal and vertical. And there are some conditions. They have to be rational, they have to be continuous functions. But these functions, these filters, let's go back to the original. They're not continuous. They cannot be continuous in the sense and differentiable because you want zero gain there. So if you go in this way, you want zero. If you want in that way, there has to be continuity, and there is no continuity because DC is set to zero. And if you take here, there is a discontinuity. But within the passband, you want continuity. So there are some contradictory or conflicting requirements in filter design. Computationally, you just go ahead and do it, and you will get some artifacts. Deal with the artifacts, thresholding. But if you want to design a stable filter in the digital filter paradigm, then there are these other considerations that come in. So I will just leave it at that. It is transformed to the Z domain through a bilinear transformation that you would have seen in 1D digital filters for each of the directions, horizontal, vertical. So you get some coefficients BM and AM, and Z is the Z domain variable, Z1, Z2 for the two directions. Bruton and Bartley came up with a design, and I won't go through that, and they gave these numbers in their publications. And we implemented them and used them, but then we found that some recursion may help. If you just do it once, you may not get the best image, but if you were to apply it again, you may get a better image. So William Ralston, who did his MSc with me, came up with a transformation to apply to change the direction. You need to take that as a basic filter and rotate it to angle theta. So he used this transformation to rotate the filter. I'll skip some of these details. Some of these conditions put in the angle band, pass band are shown there. But this is a fan filter. So with this, with the same test image, if you apply one pass, you get this with the vertical direction filter. If you apply 9 passes, you get this. So as you iterate the filter, these other bands, out of band details are suppressed, and you get a stronger response in the pass band of interest. So that was the advantage of this method. Whereas if you take the Fourier transform, apply a filter, that is one shot. You can't do anything more. Whereas with these recursive filters, you can apply again and again. Repeated passage will suppress the unwanted components and boost the desired components. Or, I think I should just say suppress the undesired components. The gain will be multiplied over and over again. So the unwanted components are suppressed. There are still some artifacts you can see. But that's after 9 passes of the image through the filter. Now Gabor suggested filtering in 1D signals. It was in 1941 or 42. His first papers were published. He suggested that the use of time-limited functions as the kernels of a transform instead of the unlimited sine and cosine. Time-limited in the sense they are still modulated with the sinusoid, but they decay. Whereas the sine and cosine functions in the Fourier transform, they don't decay, they go forever. So the sinusoids are weighted with a Gaussian function. Now the Gaussian function is also of infinite spatial extent, it goes on, but the exponential weighting factor makes them very small after some displacement, depending on the sigma value. So yes, they are unlimited theoretically, but in practice those values are so small after some displacement, you may stop at some time. Whereas the sinusoids in the Fourier transform, you cannot stop, they go forever. So there is, Gabor showed that complex sinusoidally modulated Gaussian basis function. Or you can turn around and say, is the Gaussian modulated by a sinusoid, or is it the sinusoid that is weighted by a Gaussian? You can see both ways. They satisfy this time bandwidth limit, delta t, delta f, greater than or equal to 1 over 4 pi. This is known as the uncertainty principle, and in 2D, you get this product of 4 delta functions in x and y and u and v greater than or equal to 1 over 16 pi square. So these are measures, some measures of spatial resolution and frequency resolution. In essence, what it means is, if you have a time-limited function, its frequency response or Fourier transform will not be band-limited. A time-limited function is a rectangle function. Its Fourier transform is a sinc function going forever. Not DFT, but continuous domain. If you have a time unlimited function like a sinusoid going forever, its frequency can be band limited. It will be just 2 impulses. The Fourier transform for sinusoid is sinusoid has positive frequency, positive, and negative frequency, negative value. Cosine, both will be positive. But they are band limited strictly, just in fact absolutely band limited because they are delta functions. An infinitely long time domain function is a constant, DC. Its response is just an impulse at DC. It's completely, totally band limited. And completely time limited function is an impulse, and its Fourier transform is a constant forever. So there is this duality, and the product of those will be greater than or equal to 1 over 16 pi square, which says you cannot have a time-limited function whose frequency response is also band-limited. That is not possible. You will make some sacrifices by cutting one of them. Gabor functions provide optimal joint resolution in the time and frequency domain, or space and frequency, depending on your formulation, and can form a complete basis set through phase shift and scaling and or dilation of the original basis function, or now called wavelet. But Gabor is not, we are not using Gabor as a transform. We're not getting all coefficients with all possible functions like we do with the Fourier transform. We don't need that. We can select certain Gabor functions of certain orientation and certain scale factor and use only those. It's not a complete representation. Reversal is not required in image analysis. Reconstruction of the original signal from these coefficients, if you want to call them, the filtered images are actually images. They're not individual coefficients. But we don't need an infinite collection of them, and we don't need to go back to the image domain from these components. So we can select a subset. That's what is done in wavelet analysis. You take a finite set of wavelets, and from experience or experimentation, you know these wavelets of such and such scale factor and bandwidth or frequency will be enough for this application. And you use only those. You cannot go back to the original signal from those limited components. So the set of function forms a multi-resolution basis that is referred to as a wavelet basis. That came up much later. Gabor wrote his paper in 1940s. And Dogman extended Gabor functions to 2D sinusoidal plane waves of some frequency and orientation in a 2D Gaussian envelope. And they have been found to provide good models for the receptive fields of simple cells in the striate cortex. So there is some relationship between these functions and what happens in our visual system. So let us look at a few formulations. We saw one formulation earlier. For the detection of the pectoral muscle, I showed Gabor filters as wavelets. That is one formulation, and we will see another formulation later when we talk about architectural distortion later in this chapter. Depends on how you want to implement and how you want to interpret the results. So we can say hxy, the impulse response is gx prime y prime, the Gaussian, with an exponential function, like in the Fourier transform, but this is simply a complex sinusoid. It's not the Fourier transform. It is one frequency u, one frequency y, and this is cos and sine as before. X prime y prime with reference to x and y is a rotated coordinate system with angle phi. X cos theta, x cos phi plus y sin phi minus x sin phi plus y cos phi. That is just rotation of xy to x prime y prime by angle phi. The Gaussian is this. But now, the Gaussian doesn't have to be isotropic. The Gaussian is a bell-shaped function in 1D. In 2D, it has another factor on the other side, but if you want preferred orientation, you want to detect things along a certain angle, then you don't make this Gaussian isotropic. We say we will have a bell-shaped function of this size here, but in the other side we'll make it narrow. Then that bell is squished and it'll have some preferred orientation. So this Gaussian now is not x square plus y square, but x over lambda square plus y square. Lambda is that aspect ratio. You can multiply with lambda, doesn't matter. You just define it as the inverse of this value. Multiply, divide, it doesn't matter. It's a scale factor between x and y. So the aspect ratio lambda. U and V are the center frequencies in the frequency domain as modulated by this exponential function. It is modulation in the sense that introduces a phase shift, like in amplitude modulation. Do you still study AM radio in communication theory? Yeah? Yeah, so you multiply the given signal to be transmitted with the carrier frequency, and it is shifted to the carrier frequency so the signal can be transmitted. So these are the frequency values of the modulating function. So you can say, yes, this is a Gaussian modulated using a complex exponential. If you don't want complex, you just use sine or cosine. That's fine too. So you're shifting the frequency. Gabor functions act as bandpass filters, I already showed that, with directional selectivity because of that factor lambda and theta. There is the preferred orientation implied by the fact that it is not isotropic. And the frequency is shifted by the modulating function. The frequency domain is usually divided into a symmetric set of slightly overlapping regions at octave intervals, or however you want. I showed those ellipses in the frequency domain. You want to span the full frequency domain, and you want to allow overlap between the adjacent Gabor filters so that you don't miss components in between. I'll skip some of these other details. So this is what the function looks like in as a mesh plot. So it is a Gaussian envelope modulated with the sinusoid, and in the other direction too, but they are not the same in the two directions. So you can imagine, depending on the rotation, this is broader than the other side, which is implied by this scaling. In the frequency domain, this is the kernel function, the same as an image now, bright in the middle and dark on the side, negative side lobes, bright again. So it is like a sinc function, it goes up and down, but the weighting is not sinc but Gaussian. So there are these, but you cannot see them. You can see them here. Positive, negative is going down, you can't see positive, and unless you rotate it, you won't see the negative part. But it has negative values. In the frequency domain, we get these ellipses that are sort of sections of the Gaussian located at those center frequencies, displaced by the uv of the modulating function. And the scale factor determines the size of these. So from low frequency, you go to medium to high, and you can put them at various angles. Okay. Is it a square? Or has it been stretched with? Is that a circle? It is? Okay. That's okay. Now we're not doing shape analysis, so it's okay. So multi-resolution signal decomposition becomes possible because there is a factor of this resolution in the scale factor. So you start with a wavelet, and then fine temporal or spatial analysis is performed with contracted versions. Make the wavelet smaller and smaller and smaller. Fine frequency analysis is performed with dilated versions. You want to reduce the bandwidth, then you make the wavelet bigger or slower. Then the bandwidth is reduced, and so the filter becomes narrower, and you need more of them. So you get better or finer frequency resolution. The definition of a wavelet is flexible. So in the literature, you have seen many types of wavelets. There are some requirements. The function must have a bandpass transform. There are a few other admissibility criteria. I think I've stated some of them earlier. It depends upon which of those are relevant in your application. Some may not be relevant in filtering without the need to reconstruct. So a wavelet at a particular resolution acts as a bandpass filter, including Gabor. The bandpass filters must have constant relative bandwidth or constant quality factor. This is important in auditory and visual systems. In the case of non-stationary signals, you need to compromise between how well transitions or discontinuities can be located and how finely long-term behavior can be identified. In the case of speech signals, I mentioned there are plosives that are transients. So if you use a big window, the transient will be lost in that big window. So you want a small window. But if you use a very small window, you'll be looking at maybe one of the wavelets of the repetitive function in the case of voice speech. You're not looking at the entire voiced signal. So there are these conflicting or contradictory requirements, and that is related to the uncertainty principle. So you use multi-resolution. You use wavelets of multiple durations, scale factor, and then try to put all the information together and analyze the image with information related to fine detail and coarse detail. Similar to the short-time Fourier transform that is used in speech signal processing, we can apply a window function to the image, fxy, multiply with a window. The window could be rectangular, square, Gaussian, whatever you want it to be, and then the Fourier transform. This is the short-time Fourier transform. You are computing the Fourier transform not only as a function of frequency uv, but also spatial position x prime, y prime, where that window is located, centered. So that window selects a certain part of the signal or image. The Fourier transform kernel is the same as before. So you compute this for each position of the window as the window is translated, commonly done in speech signal processing as the short-time Fourier transform. Not the Fourier transform of the full signal, but little windows. So in the case of the 1D signal, if you have a 1D signal, take the whole Fourier transform, you get one spectrum. But if you take the short-time Fourier spectrum, short-time Fourier transform, you get as many Fourier spectra as the number of window positions to scan the signal. So it's a 2D function. Now the image is 2D, the displacement is in 2D, so the spectrum is a 4D function. There are some advantages. You are addressing non-stationarity. The signal is changing over time or space, so you are taking small portions and getting the spectrum of what is present there. But then the same window is used at all frequencies, and the resolution is the same at all locations in the resultant space. So that, again, the uncertainty principle says you cannot have arbitrary resolution or arbitrarily fine resolution in both space and time, both time and frequency or space and frequency. If the window function is small, the large-scale behavior is lost. If the window is large, rapid discontinuities are washed out. So there is a compromise everywhere. So this is where the notion of scale is introduced. By varying the window function, one will be able to identify both discontinuous and stationary characteristics. So in speech signal analysis, as long as same speech segment is produced, same phoneme, as it is called, is produced, like ah, you have the same window, keep growing the window, and when it changes, like ask, and s comes, then you say, I'll stop the window, start a new window, and then asterisk t is a plosive, so it'll be a small window when it starts and stops, and so on. So adjust the window size depending on what is present in the image or signal. So you can call that multi-resolution or multi-scale analysis of the signal. So 10:30 is the coffee break, is it? Okay, let's take a break here. We'll come back. There is more on this. We will continue in 30 minutes. Thank you. Gabor functions Now, as I said, you can form a wavelet basis. The wavelet basis is given by a translated and scaled version of some basic mother wavelet. H is the mother wavelet, x prime, y prime, lambda 1, lambda 2 are some parameters. The factors lambda 1, lambda 2 can stretch or expand or shrink the function, and x1, x2, xy, y prime are the shift parameters. You can also put a rotation. If you want to call it as a wavelet transform, then you can compute these coefficients for the parameters just by taking the projection of fxy with each of these wavelet functions with a normalization factor. So you have contraction, dilation, translation of the basic mother wavelet, and rotation if necessary. So in the formation of a Gabor filter bank, we need to make some small modifications. William Ralston did his master's thesis on this topic with me. The real component of the Gabor filter acts as a matched filter to detect broad directional components, assuming that the components are brighter than the background, the cosine function. Otherwise, you use sine, or you reverse the image. The parameter sigma specifies the spatial extent of the filter. Lambda specifies the aspect ratio of the filter that modulates the sigma value. If lambda equal to 1 and the phi parameter is not specified, then it is isotropic. So it can turn into just a simple bandpass filter. In the frequency domain, this results in an oriented filter occupying the middle subsection of the corresponding ideal fan filter. It is a fan filter, but it is taking a part of that fan filter as a bandpass filter depending on the scale and the orientation given by tan inverse B over U. So these specify the Gabor filter bank. Now, how many of these you need depends on the resolution of the details you want to capture, the size of the objects you want to capture. So you don't go minus infinity to infinity. That's just a theoretical convenience in representation. So there are some parameters that we used. For this test image, we used only those 4 angles. So you may convolve the band-limited and decimated versions of the image with the same analyzing wavelet. When you do multi-scale analysis, there are 2 possibilities. You keep the image fixed and change the wavelet scale. Or you keep the same wavelet and downsample and shrink the image, change the scale of the image. So 2 possibilities exist. But if you're given a small finite-sized image, then you can only shrink it so many times. After that, you lose all details. So one needs to be careful in the application of scaling to the given image. Now, when you have a Gabor filter bank, you could take the output of each one of them, or you may combine them using some vectorial addition of the components. Vector in the sense, the output of each Gabor filter is an image with some pixel values. But there is an angle associated with that image because an angular filter was used. So you take the angle of the filter that gave that output as the phase or angle, and the pixel value in the output as the magnitude, and then it's a vector. So each pixel can be treated as a vector in the output image, and at every pixel you can compute a vectorial sum of the components you have obtained. So decimation and filtering at each scale will provide you these images, and you may need some interpolation of the decimated and convolved images because you have downsampled them. You have to go back to the original size, and then they can be added to obtain the overall response, added either directly or using the vectorial format. The vectorial format is this. Suppose you have 4 components. For the synthetic image, we only had 4 components. So 0, you get that response for the horizontal filter. 45 degrees to get that for 1 pixel. 90 degrees and 135 degrees, do a vector addition. That is, copy these vectors and add them all up, and you get that as the output. So this is the vector addition. You're copying this vector here, that here, and this here. Complete the polygon. So the output at that pixel has this angle, some, let's say 40 degrees or so, and that magnitude. This is advantageous when you want to do directional analysis of an image with components at various angles, and you're using only a few filters at a few different angles. In this image, we only have components at 0, 45, 90, 135. But suppose your image has components at all angles, but you don't want to use 180 filters, one for each degree. So you may say, I will use 6 filters, equally spaced 0 to 180. But the angles could be in between the filters' angles. So then you do vector addition, and you get the actual angle by interpolation of these output values. So here we have the same test image, Gabor filtering at 0 degree or horizontal with 1 to 1, 2 to 1, and 4 to 1 decimation. When you decimate 4 to 1, you see the thick bands are obtained. When you have 2 to 1 decimation, or even the original 1 to 1, the thin bands, these thin lines are detected. But they are not detected here, in the sense the response is low. So when you do decimation of the image, then you are taking into account the variation in the size or scale or thickness of the objects. Some get detected at some scale, some others get detected at other scales or give a high response. When you add them all up, you get this output. Now, none of these is perfect, of course. It depends on the nature of the image, the quality of the image. Decimation in the image causes loss of resolution, loss of clarity, and could cause other artifacts. So this is a sort of a mathematical possibility and notation, but in practice you may rather change the scale of the wavelet. That may be better than downsampling of the image or decimation. We did multi-scale edge detection using zero crossings that I showed earlier. My postdoc fellow, Jixiang Liu, he did this work with the log filters, Laplace-Gaussian filters, and got zero crossings and got that map. I won't go through this detail. If you want, you can read this later on. It includes a number of very specific conditions for that kind of image to find the two sides of a potential rectangular pattern or line pattern, and getting the width and so on. So I will skip all of this, how to find opposing edges of a given line pattern, and I'll just go to the next section. There are some images I'll show later. Now we saw that the Huff transform can be used to detect lines. The radon transform that is used in computer tomography involves projecting an image at various angles. So there is an angular dependency of the projection and what you compute there. So the radon transform contains some information about angular distribution if you were to take the radon integral at multiple angles, which is done in CT and MR reconstruction. There are some similarities between the Huff and radon transform that you could use to advantage and combine them and come up with a combined Huff-radon transform. My master's student, William Ralston, came up with this transformation and came up with this implementation of the two transforms together. We have done some other work also for the detection of the pectoral muscle and the nipple using such transformations later. But Ralston wrote this paper on combining the Huff transform with the radon transform. The Huff transform is primarily applicable to binary images in the sense you must first detect the pattern and you are required to have a binary image where every pixel contributes to the output, to the transform, Huff transform domain. So there is a detection step required first, edge detection or line detection or something. I did mention in the detection of the pectoral muscle that the incrementing of the accumulator need not always be by 1. It could be incremented by the intensity of the output in the detection process. So it is possible for the input to have some grayscale variation, but you don't put the original image directly. That doesn't help with the Huff transform. With the radon transform, you take the original image and integrate at various angles using straight lines passing through the image at multiple intercepts or displacements for the same angle for parallel beam projection. In this book, there is a separate chapter on image reconstruction from projections where I have described the radon transform and reconstruction from projections. So the results of the Huff transform are dependent upon the binarization method or the detection method to segment the image and get the patterns. So we said we use rho equal to x cos theta plus y sin theta as the equation of the line. Any straight line is bounded in angular orientation by 0 to pi and bounded by the Euclidean distance to the farthest point on the image from the center, assuming the center of the image is the origin. So we saw that for a given point xi, yi in the image, we obtain a sinusoidal curve in the Huff domain rho theta. So rho naught equal to xi cos theta naught plus yi theta naught. So each point xi, yi lying on a straight line with rho equal to rho naught and x equal to x naught in the image domain corresponds to this sinusoidal curve in the Huff domain. For each point in the image domain, the Huff transform performs a one-to-many mapping, resulting in a modulated sum of sinusoids. So all of these sinusoids are added up for pixels along a straight line. It is a kind of an accumulation procedure, also called as a voting procedure. Each pixel contributes a vote. Am I on a line or not? What are the coordinates of my line, of the line on which I exist? So in the Huff domain, we do peak detection. We saw that. If you look at the Huff transform, that line is indicated by the theta angle of the normal to the line and the distance along the normal from the origin to that line. In the radon transform, the same line is defined. The origin is taken to be in the middle of the image. It doesn't matter, some origin. And then you integrate the image along that ray. You call it as a ray, like an X-ray. X-ray photons are going along that ray and they get attenuated as they pass through the medium. And then you get one ray integral. You displace and then get that kind of an integral for all rays at that angle. If you use some of the scanning geometry, you can rebin the measurements to parallel ray geometry if you wish, or do reconstruction directly. There's a problem with the Huff transform with crosstalk. I mentioned that if a line is of 1 pixel thickness, it gives you all those sinusoids, they intersect at one point. But if a line is thick like this, it's a rectangle. There are many pixels in this rectangle, but you can form many lines by connecting many pixels. So there could be lines of various angles within that thick object, which is not a line, but assume this is a line. then I can draw so many lines connecting various pixels. I can even draw a line this way. So this thick rectangular line contains lines at various angles if you go one pixel at a time, and that's what we could call crosstalk between multiple straight lines in the Huff domain. If the image contains several lines parallel to the x-axis, they correspond to several peak lines in the Huff domain at different values of rho for theta equal to 90. But then points at in the direction perpendicular to that at theta equal to 0, you have a number of lines. I can take this point and this and connect, and that is perpendicular to those lines. So I get false lines at other angles. So this is an illustration of crosstalk. I have a number of lines that are horizontal in this case, but I can take pixels there and join them. These lines are broken, but still, the Huff transform counts this, all of them together and gives you a line. Says there is a line with so many pixels in this direction, which is orthogonal to those lines. And you detect all of these lines for all of those pixels. And if you have a thick line, as I said, I can draw so many lines within that at various angles. So you get a spread. So you combine the Huff and radon transforms. The Huff transform may be viewed as a special case of the radon transform, but the origin could be shifted. Now you could define the Huff transform with the origin in the center of the image also. You just shift your equations. In programming, previously in Fortran, you were not allowed negative indices, you were not allowed 0 index value. Some languages like Pascal started allowing, I could say, minus 50 to 50, including 0. And then came other languages, some of them allow negative, some don't. MATLAB doesn't allow 0. MATLAB, you have to go from 1. So we are back to Fortran type of indexing with MATLAB. When we were writing programs in Fortran, it was being criticized, well, I can't handle the origin as 0. Or I want my time to run from minus 50 to plus 50. That was cited as some big drawback, but now MATLAB is big and we have the same problem. Pascal allowed that, and C, I don't know, doesn't allow. Does C allow negative index? No. 0? 0 is yes. Okay. So MATLAB doesn't allow those. So that's one of the problems, but it doesn't matter. In your computation, you just adjust the equation. So shifting the origin is not a big deal. So in the method that Ralston developed with me, the Huff-Radon hybrid transform is computed by updating rho I theta I by adding the pixel intensity and not by incrementing 1 as in the Huff transform. That's about the change. There is no big difference. We already did that in the detection of the pectoral muscle. We did in the sense I described that, but this work by Ralston was done a few years before the other work. So a line here gives you a bunch of sinusoids like you have seen before. And the incrementing is done by the intensity. In directional analysis, it is of interest to obtain the number of pixels or the percentage of the image area covered by linear segments in a particular angle band. That is what we want. So we need to form another parameter space with the number of pixels. Here the intensities have been added up, but you don't know how many number of pixels are there. So you need to have another space, like the Huff space. The shadow parameter space is the Huff transform of the image with no threshold. So you need to have another measurement. So here we have an image with 5 segments, and we have the Huff-Radon space. There are these points where these curves are intersecting, but note that these are thick line segments, so these areas have regions of intersection, not single points, spread over. Now, which peak do you detect? Of course, you can say, in that region, I want to find one peak and take that one parameter. But if you just compute the angular distribution, we get this, which is not very good. There are only 5 angular components, but I'm getting such a big spread. So this method has its limitations. We filtered the Huff space to detect these regions and eliminate others so that the search in the Huff space, Huff radon space, could be made a little better. So we call these butterfly patterns, and we could search for that. So filtering and integrating in the Huff radon space. So there are some methods given in the literature, 3x3 filter to locate the maxima in the Huff space and connect collinearities, that is pixels that are along the same line, in an edge image space. In our work, this concept of a butterfly was used, and you could manipulate the pixel values of filter using this concept. The filter used is this, which is a kind of a derivative in one direction and smoothing in the other direction. Let me see if I can. With more complex images, things get more messy. This is a collagen fiber electron microscopy image. We can see fibers, but they are not clearly separated. So practical images pose more problems than what we can imagine and simulate in synthetic images. So the Huff radon space is this. Very complex to detect peaks. What are local peaks here? So the lines are thick and there is some other substance in between. The lines are not clearly defined. You could take a derivative of this and so on, but perhaps Gabor filters will help, as we'll see later on with mammograms. So this is the filtered Huff radon space, and hopefully that will help in detecting peaks, local peaks. And if you were to use that information and make your measurements of the line thickness, then we get this rose diagram. It shows a large component here at this angle, a little less than 90 degrees, so that is okay. There is some dispersion here, but all of these are false. Are there horizontal fibers here? Maybe a little piece, but I can connect all of these and draw horizontal lines that are not in the image, but the algorithm will connect these high intensity pixels and cause the artifacts telling, well, there is a horizontal line there. So these are some limitations of the methods. All methods have limitations. We can formulate additional filters and techniques to reduce these, but this hasn't worked well.
So we are setting the angles. So this method, are we setting the angles or are they being automatically?
Which one?
In this one,
Yeah.
it is going under different angles, right?
Yeah.
But are they being settled, we are setting it, or it's being detected automatically?
Well, the angles are measured automatically from the Huff radon space. The angles are obtained, one of the axes of the Huff domain is angle, and the other is number of pixels or added intensity.
Yeah, but then Gabor filter, we are setting up the angles, right? Like, so,
Gabor filter, you get the image itself. You get a filtered image. I'll show you that.
but we are setting up the angles over there, right? And the Gabor
We set the angle, correct.
here we are not setting.
No, here we're not setting, well, setting in the sense, it is implied in the Huff space. The coordinate along one of the axes is angle. The other is number of pixels or intensity. So yes, we are setting, but we are allowing it to span the full range, 0 to 180. And Gabor filters, I have to specify the angle for each filter, and I have to apply the filter and get the output. Here, all angles.
But
But you can specify, you can say that I want it only from minus 70 degrees to plus 70 degrees. If you know that your patterns of interest are in that range only as we did for the pectoral muscle. We didn't go 0 to 180.
So it can be either angle, right? Either x.
No, one axis is angle, the other is the number of pixel counts or intensity. Whether it is this way or that way, it's your formulation.
Angular bands can be specified, like suppose here 0 to 91 to 560.
Oh, the Rose diagram, there we bin it. Okay. The Rose diagram is obtained by binning, by including all components in that angle sector. I don't know how many do we have here. 1, 2, 3, 4, 5, 6. So 15 degree bands. So we don't plot the output for every degree. It'll be very noisy. So 0 to 15, they're all put in that one band. The same for other Rose diagrams I've shown you. You can specify 10 or 18 or how many other band bins you want for the histogram. Histograms always have bins. In the case of gray level, you only go one level at a time, 0, 1, 2, 3, and so on. Here, if you go 0 degree, 1 degree, and so on, you may not get many pixels. And also, you may not have that resolution in your computation. So you use larger bins of 15 degrees each. Okay? These results are far from perfect. So let's look at a few applications now. These are all the methods. In my book, the first few sections are methods, and towards the end, I have biomedical applications. Sometimes those sections also have some equations and methodology. So I've already said ligaments are highly organized connective tissues that hold bones together across a joint and hold the joint together. They consist of nearly parallel arrangements of collagen fibers that are attached to bone on both sides of a joint. Now, nearly parallel, but there is a wavy nature to that, like the strands of a rope. A rope doesn't have all strands straight. There is it is twisted. They are intertwined. But if you take a small section, the strands of a rope or a rope, whichever material it is made of, will have straight lines. So injuries to ligaments are common due to sport. In Canada, it is ice hockey. It could be soccer or football. Cricket also, they run. If you fall and twist, then the ligament could be ruptured. And unfortunately, they don't heal. They don't heal well because the ligaments normally don't have blood supply going inside the ligaments, because if you have blood supply inside and there are vessels with liquid, then the ligament doesn't have the strength. So when there is injury and ligament is ruptured, or it is, in this case, in our studies, they were ruptured surgically in rabbits, the healing process starts. And the healing process is facilitated by more blood supply. New blood vessels develop and collagen is deposited. New collagen material forms in the injured area and scar tissue develops. And scar tissue will not have the same organization of collagen fibers as in the normal case. Slowly over time, over a month or two, the organization changes from disorganized random distribution to an organized distribution that tends towards the original distribution, but not always, not perfectly. And also the blood vessels that came in, that were developed to facilitate the recovery process or the healing process, they go away after that healing process is complete, and the number of blood vessels and their thickness will reduce so that the ligament can bear load. That is inside the ligament. But epiligament, that is just outside the surface of the ligament, will have more blood supply, more blood vessels than the core of the ligament. So the injured or healing ligament or injured or healing joint may become loose or unstable because of lack of support through the these ligaments, because they are torn or they are still healing. This was done in collaboration with Dr. Frank, who was a famous orthopedic surgeon, and his colleagues in Calgary, and Dr. Subhashish Chowdhury, as I mentioned, the previous director of IIT Mumbai. He was my MSc student at that time in the 1980s. So a critical factor at that time in studies through observations that was thought was that blood supply is important in healing, and the organization changes. And the reorganization or remodeling of collagen fibers is important in gaining strength back in the ligament. Okay, I think I said all of that. The process used, if you refer to the first chapter, if you go through the section on electron microscopy, the ligament itself is taken out of the rabbit, and it is frozen and fractured. The 3D ligament, it's very thin, of course, it's maybe a couple of millimeters thick and a few millimeters long, frozen and fractured. So the fractured surface shows the collagen fibers. There is some process of coating with various material, and then it is scanned using electron microscopy. The surface is scanned, so we get a picture like I showed earlier with the collagen fibers. So we did directional analysis using sector filtering, using that weighted fan filter with the cosine function in the Butterworth and linear filters. We obtained directional components over 12 angle bands spanning the range of 0 to 180. So each angle band is 15 degrees wide. So here is an image where you can see some of these oriented components clearly. And the binarized and directional components for the angle 75 to 90 degrees. So that comes here. You don't see the other components here. These come in the 0 to 15 degree band. So these were thresholded. We used Otsu's method and a few other methods to find the optimal threshold. So these are thresholded binary images. You count the number of pixels, multiply it by the pixel resolution, but that's a constant scale factor, and get the angular distribution. So you can see that most of the fibers are running close to vertical. This is 90, 75 to 90, 60 to 75 degrees. The other angle bands have very little in them. So this agrees well with that image. In the case of scar tissue, this is for 75 to 90 degrees, 0 to 15 degrees. It's a little hard to see orientation here visually. But a computer algorithm will say, oh, okay, well, look at that. That is horizontal. Look at this, it is horizontal. And so on. There is a piece there. So within that, you get whatever is horizontal. And now it has a broad distribution, nearly uniform. So this is scar tissue. We were given a number of these images. In those days, the electron microscope pictures were taken on film and printed on paper, and then we had to scan them using a TV camera. It was a TV camera which had 380 by 440 pixels or so. Very poor resolution, but that was the state of the art then. There was a big cable going from there to the computer in the AC cool room, and that introduced a lot of noise, which is what you saw in that clock image. If you remember that clock image, that was a clock in our lab. We took that picture with that TV camera and the digitization frame buffer in the computer room. With the cable having so many BNC connectors and other connectors, there was a lot of noise. So that was a real noisy image showing how much noise was introduced in this process. And the resolution is poor, and these are prints of scanning electron microscopy images. So there were a number of images. Unfortunately, many rabbits have to be sacrificed in this case. And by the way, the Foothills Hospital and most hospitals, perhaps here too, they have an annual event or an event quite often where there is a kind of a ceremony to thank all the animals that gave up their lives. They do that in Canada too. So there is a process to acknowledge that some lives were taken of lab animals to create data of this kind. Unfortunately, destructive. So the procedure was, the rabbit was taken and its ligament was ruptured surgically, and then it was allowed to heal. And the question is, what is the healing process? Do you want the joint to be immobilized in a cast? And for how long? Like if you break a bone, then you put a cast. But for how long? How many weeks? Too many weeks, then your muscle will atrophy and you will have problems in regaining strength. Too soon, the bone will not have healed and will not have the strength. And there may be other methods of facilitating recovery. Which method is the best? So how do you characterize that and determine objectively what should be these parameters for treatment? So that was the question here. So after injury inflicted surgically, the rabbits were allowed to heal, one by immobilization of the joint, like a cast, and the other, they were let free in the sense they could use that joint without any restriction. And here we have images of individual single samples, 3 weeks after injury, that is 3 weeks of recovery, 6 weeks and 14 weeks, without immobilization of the joint after injury. And here, 3 weeks, 6 weeks, 14 weeks with immobilization of the affected joint for 3 weeks. So you see that if you do not immobilize, at 6 weeks there is not much organization. 3 weeks there isn't much organization at all. The joint has been free after injury. 6 weeks there is some recovery, 14 weeks there is some more orientation. But these are different rabbits, different ligaments. One sample, once you take this out from the rabbit, that rabbit has to be sacrificed. So here there was immobilization for 3 weeks, and at 3 weeks there is already good alignment at a slightly different angle, that doesn't matter. And 6 weeks and 14 weeks. 6 weeks there is very clear alignment. So this is the collagen remodeling process in individual images, one image of one ligament of different rabbits. For each ligament, many images were taken, and there were a few rabbits involved in each of these. So these are the composite rows diagrams of a number of images and a few rabbits. I don't, those numbers are there somewhere. So on the left-hand side, without immobilization. This is with immobilization for 3 weeks. So if you don't immobilize the joint at 3 weeks and 6 weeks, there is still full random distribution. At 14 weeks, it looks good. If you immobilize for 3 weeks, there is good alignment already, that gets better and better. At 14 weeks, both of these are same, which means after 14 weeks, the ligament is healed regardless of your treatment process. In terms of this, whether the rabbits were happy or not, that's a different question. But the alignment looks good. But you reach this faster if you immobilize for 3 weeks. So that's the conclusion. This is objective analysis of the recovery process and comparing two different methods of treatment. And we did 3: immobilization for 6 weeks also. So 3 weeks immobilization, you are there, and let me make sure. Here. This one is 3 weeks immobilization. From there, at 6 weeks you are here, and then you are the same, meaning the entropy of that distribution Without immobilization, 3 weeks, the entropy is large. 6 weeks, the entropy is large. 14 weeks, it comes to this normal band. This is the normal mean plus standard deviation. 14 weeks, the 6 weeks of immobilization, there is nothing for 3 weeks because it is immobilized for 6. You're already in the normal band. And 14 weeks, it remains the same. So this says not immobilizing is not good. Immobilizing for 6 weeks is not required. Immobilizing for 3 weeks, it's already in the normal range. At 6 weeks, it's in the same range as same entropy as for immobilization for 6 weeks. And at 14 weeks, they're all the same. So of the three then, the best is immobilize the joint for 3 weeks. Now some of these perhaps were established by clinical practice. But now we have objective, quantitative analysis to support that practical, experiential observation with quantitative image analysis. Yes, a number of rabbits had to be sacrificed in the study, but that is how clinical research is done. Okay. I skipped some of the details about the Huff-Radon transform and analysis using edge detection. We did that, but the results were not great. And those formulations are a bit too lengthy. You could read that yourself later if you wish.
Will that be a part of the test then?
Whatever I skipped will not be part of the test. Anything that I skip will not be part of the test. Anything that is too specific to our research project will not be part of the test. But general concepts. I say I'm telling a story and you should be able to get some sub-stories and tell them with a few equations as scientists and computer engineers and so on.
Questions from each chapter that you have.
I'm sorry, I didn't get you.
Example questions from each chapter.
Well, if you had the book, you would have those at the end of the chapter. How will you get it?
Quantitative problems also included?
Yes, simple, something you can do by hand. If you were to, did I put them on my website? If you go to rangayan.ca and there is the image processing, under my image processing book, I think there is something called tests and exams. All old tests and exams are there, some with solutions. I think I have put it up there. I need to connect to the web to check if it is there. Under my, if you go to the course, not the music, not that, you want the other one. Yeah, but that's within that you go to the engineering one and keep going, and the book, table of contents, biomedical image analysis, and there's some teaching learning material somewhere. Where is that? Maybe I haven't put it up. Teaching files. No. Just a moment, let me search if I have put it here or not. Previously, my website, I had that, but then the university changed the websites. This is my own. I thought I put all the... Yeah. Tests and reports, zip file, image files, zip file. You'll have to download a zip file. So under my image processing book, there is table of contents and updates and corrections, tests and reports, image files that you can download, but these are zip files. I couldn't put multiple files in this. So there is a zip file. If you download that, you will get a whole bunch of previous exams. But those exams are for students taking my course, and those questions may not be relevant here. This is a rapid course. There it is a slow course over 3 months. So some of those questions may be, how should I say, more difficult than what I would ask here. I would give simpler questions here than what you will see there. Okay. So if you go to my website and go to the engineering part, and then under the textbook biomedical image analysis, you will see links to download some of the test images that I have used in the book, and tests and exams, and some seminars also. PDF files of my lectures are there. Okay, let's look at another application with ligament healing again. Dr. Bray, a colleague of Dr. Frank, and Dr. Frank himself were engaged in this project, and this was their project, and we contributed the image analysis part. And Kevin Eng did his research project with me and developed these methods and results. These are microscope images, regular microscope images, light microscope images of ink-stained blood vessels in the rabbit medial collateral ligament. I showed you one of those ink-stained images. The normal ligament is relatively avascular, that is, there are not many blood vessels, and there are a few blood vessels, and they are along the long axis, parallel to the long axis of the ligament. Scar tissue after injury has more abundant network of blood vessels to facilitate healing, and they don't have a preferred orientation, they are not aligned. So this is the process. The picture has come here, similar to what I mentioned earlier. Small differences. This is the knee joint of the rabbit. The ligament is attached there and here, and sutures were put there, and this part was removed. And it was removed after vascular injection of the India ink, as it is called, black ink. And then scar tissue develops, and because the ends are marked by sutures, this scar part is taken out. The original ligament is there in the scar extracted sample. Mid-substance scar is here. And using a microtome, these were sliced to a resolution of, if I remember, at 10 micrometers, thickness of 10 micrometers. So the images look like this. In a normal ligament, this is the long axis of the ligament, there could be a few small blood vessels, and they are parallel to this long axis. After injury in the scar tissue, this is 17-week scar, blood vessels go in different directions. Now this is a destructive way of imaging a 3D sample by cutting it into thin slices and then observing, like a slide, pathology slide, biopsy sample slide, observing under a microscope and taking a picture. Now we may say, well, do 3D CT imaging, but the resolution required here is of the order of 1 or 2 micrometers. Blood vessels are just a few micrometers thick. That is a bit difficult to get even with microcomputer tomography. And the samples are very small. So that was the technology then, anyway, in the 1980s. So the binarization was a problem. With images like this, binarization is a bit difficult because there are very few pixels corresponding to the blood vessels compared to the background. Earlier I talked about bimodal, multimodal histograms or unimodal. These histograms are unimodal because there are so many pixels of the background, very few pixels of the object. So Kevin Eng, who did this project, had difficulty in finding an optimal threshold. So the derivatives were obtained in the horizontal and vertical directions, and the maximum of the 2 derivatives were taken, and then they were summed, and there was another sum computed as the derivative weighted with the original image, and there is a threshold known as the Rutherford-Appleton threshold, which is the ratio of the two. Otsu's method I skipped, but you can go through the derivation of Otsu's method later on. There is a method known as maximal histogram concavity. I mentioned there could be two peaks, like Gaussian superimposed, and in between there is a valley. Find that point of minimum value in the valley, which is concavity between the two peaks. So that is maximal histogram concavity. You can also find peaks by identifying the convex hull of the histogram. And histogram concavity at any gray level is defined as the vertical distance between the convex hull H bar and the actual histogram edge. So there are so many of these methods. I'll show the method here graphically. This is one of the original images. There is a lot of noise. The background is not white, but there is a lot of noise in the background. We want these black pixels, which are the blood vessels. After binarization, we get this with a few little other pieces, but those are not false. There is something there. Now we should note that in the ligament, the blood vessels go in all directions. And if you slice them, blood vessels would have gone through multiple slices. And when you cut them, you get just a cross-section of the blood vessel in a given slice. So you will get some artifacts like this, and blood vessels may not go vertically across the slices, but they will weave in and out. They'll be going in and out like that. And when you cut a blood vessel that is curving like that, you will get a small section of that, perhaps like this. So there are artifacts in this process. True 3D reconstruction would be the best, but it's not feasible at this resolution and with this sample size at this time. Now there is microcomputer tomography possible by using synchrotron radiation. In Canada, we have what is called the Canadian Light Source in Saskatoon, not far from Calgary, maybe 700-800 kilometers. It's a huge facility, huge building with an accelerator, not linear but circular, synchrotron. The chamber where the accelerated electrons run is about the size of this room. And there's a big circular donut kind of a building with the chamber approximately of this size. So it's a huge facility, and there's only one in Canada. And at certain points along that electron beam, you get certain types of radiation emitted. And you can get X-rays at a certain specific frequency. And then you can perform tomography, but unlike the CT scanner where the X-ray tube rotates, here the X-ray tube is that huge building. It cannot rotate, so your sample has to rotate. The beam is fixed. Your sample has to rotate and translate. So if you have small samples, you could use that and get resolution of the order of a few micrometers, but you have to make many measurements. Or you can also scan parts of a big animal like a horse that you cannot put in a CT scanner, where the horse has to stay fixed, or somehow you put it on a table that rotates. Yeah, the horse has to be rotated. The beam is fixed. So some arrangement has to be made to obtain the radon transform at multiple angles. There, it is possible to image small samples as well as huge or large samples. But we didn't have access to such facilities then. So how do we get this? The histogram looks like this on log of the histogram. There is a peak here. This is the dark side. The blood vessels are here. This is the background. So the background is much larger than the blood vessels. And the convex hull of the histogram is that. The convex hull is the smallest convex object that completely includes the given object. And it is convex in the sense if you connect any 2 points inside the convex hull, that line must be inside or within the convex hull. So that is the convex hull, and you find the, by the way, the Rutherford Appleton gave this threshold. That is not good. Concavity gave this. There is another minimum, the minimum, what was that? It's somewhere there earlier. Anyway, that's another threshold. So we finally took the average of these two, which is somewhere in that. There is noise here. We could have smoothened the image, but so even on a log scale, the two peaks are appearing comparable, but the number of pixels in the background is that much. Then we wanted to perform skeletonization to get the angle at every pixel. So if you take this image, it's a bit hard to find the angle. So if you can just find the skeleton, then at each point we can find the orientation by getting the tangent. The diameter at each skeleton point was obtained by taking the minimum of the distance between the set of contour pixels and the pixel SI. So we saw the skeletonization earlier, so I don't need to go through that. This is the skeleton for the other image I showed earlier, or one of the images. For directional analysis, for every pixel, you fit a straight line using a small window, like a moving window. You fit a straight line, and the straight line approximation is given by this best fitting straight line, sum of xi, sum of yi minus sum of xi yi, normalized by this mean squared value, the square of the mean value and mean squared value here. But we turned it around. If the slope becomes very large, then that fitting method fails. So we took the inverse of that. 1 over m is given by this quantity, and this worked better. So you are just getting the slope, but the inverse of that. At each pixel on the skeleton, we drew the perpendicular and found the distance of shortest pixels of shorter distance on the edges, and got the diameter or thickness of the blood vessels and the area at a given angle, area of the blood vessels for a given angle. And W theta is 1 over cos theta or 1 over sine theta, depending upon angle being less than or greater than 45 degrees. So these are some of the distributions we obtained. Now we have rotated it to go minus 90 to plus 90 degrees, because this is the long axis of the ligament. So this is for normal ligament averaged over 82 images from 4 ligaments, that is 4 rabbits. And this is 17-week scar tissue from 3 ligaments, 115 images. So scar tissue has a broader distribution. Here the binning is finer. We were able to get the angle finer. The filtering angle bandwidth was bigger at 15 degrees. Here we got, I don't remember, I don't want to count how many bins. It's somewhere. So we have finer, maybe 3-degree bins or something, or 6-degree bins. So this is the Rose diagram for a normal ligament, blood vessels now. This is for 17-week scar. So we characterize that using measures of dispersion or variance, entropy. They give similar values, variance and entropy, from different perspectives, but the curves showed similar behavior. So some statistical analysis was done, and a number of images were obtained from a number of ligaments. The entropy values were computed, and standard deviation of those, and percent vascularity, that is area covered in the image. And then a number of assertions were made with certain confidence levels that were computed. The V is vascularization. Vascularization in normal is less than that in the contralateral. The contralateral, that is if the right knee ligament was injured. Then the left knee ligament was also analyzed. And there is a contralateral effect. If one side is injured, there is an effect on the other side, possibly because the rabbit is putting more load on the other side. So there is an effect on the other side with a confidence of 70%. Normal, less than mid-substance scar, high, 96% confidence. So he chose to do statistical analysis in this manner, and so on. Compared to the epiligament, that is the layer outside the central core ligament, normal is less than, volume of vascularization less than contralateral is 99%. Less than original ligament and 70%. And H is entropy. Entropy of normal less than mid-substance scar, 99%. So very clear. And there are a few others. Essentially, as I said at the outset, in the core of the ligament, there are not many blood vessels in the normal case. And of the few blood vessels, or the few blood vessels that do exist, run neatly, parallelly aligned with the length of the ligament. In response to injury, more blood vessels are formed, and they don't have that parallel structure. So volume of vascularization increases, the entropy of the orientation distribution increases. And then as the ligament heals, it goes back towards normal, but may not reach exactly the normal parameters. Okay? Detection of breast tumors. This was the PhD project of Naga Mudigonda. At that time, this was 99, I think, 98 or 99. At that time, detection of masses in mammograms was a big research topic with many, many researchers around the world working on that. The typical sensitivity of detection was of the order of 80-85%, with 2, 3, 4 false positives per image or more actually at that time. The aim was to get it to about 90-95% with 1 or 2, maybe less than 1 false positive per image on the average. That was reached much later, some 20 years later. Perhaps now it is in that range. As engineers and scientists, we quote these factors. What is the sensitivity of detection? That is the percentage of the tumors that you detected. And how many false positives did you mark per image on the average to achieve that sensitivity? If I say every mammogram has a tumor, I'll get 100% sensitivity. But a large number of false positives. That doesn't help. And if I'm too restrictive or conservative in detecting tumors, I can reduce my false positive rate, but I'll miss tumors. My sensitivity goes down. So there is always that compromise. In practice, a radiologist may tend to be cautious in the sense, if there is suspicion, the radiologist may say, let's get more tests done before sending for a biopsy, because biopsy is painful and could cause some other problems, infection and pain. So there will be additional tests like ultrasonography, maybe MR, whatever is available. But if a tumor is missed, then the cancer continues to grow and the patient suffers. And the treatment that is required later when the cancer has metastasized would be more radical or cause more serious problems. So there is always this trade-off. Which side you want to be on depends on the clinic and the preferences of the radiologist, and whether it is a screening program, diagnostic program, who pays for the costs, and so on. In Canada, we don't pay anything. We pay taxes. The money is taken, as I said, before it comes to my pocket. The government has 40% of the money. We get health care, but we have to wait. So there is that. The government controls it. And there's a long wait to get into an MR machine, maybe 6 months, maybe a year. If it is an emergency, things happen right away. If I'm dying, they say, okay, don't die, we'll fix you. But if I simply say, I have a pain here, they say, okay, we'll take care of you maybe next year, slowly, keep observing. Depends on that. But I can go to a clinic and say, I have a pain here, and they will put me in an MR scanner here right away and charge me, I don't know how much. My numbers are still in terms of 1980, when I used to get, 1976, I used to get 400 rupees a month in scholarship for my PhD. I don't know how much it is now, 10,000, 20,000 or something. 40,000. After PhD, I got a job, temporary job of as a research associate, project assistant for 700 rupees a month, and I was happy. And now you want at least 1 lakh, maybe 2 lakhs a month. Okay, those numbers are different. I don't know how much an MR scan costs here now. But that's the question of sensitivity versus false positive. In Canada, the tests are free, but I have to go there and get the test done. Here, the tests will cost you money. Every test will cost you money. So you have to pay if there is something suspicious. So when the radiologist says, well, I think there is something suspicious, go and get this test done, you have to pay. The radiologist may say, well, let's wait. But then who knows? There may be the cancer, and it could get worse. So that is the issue in sensitivity versus false positive, or specificity. When one doesn't have the disease, it must be correctly diagnosed. Otherwise, asking for more tests means, again, more cost and needless pain of going through all those tests. So in this method, we develop first wavelet decomposition and low-pass filtering, and then find iso-intensity contours via adaptive density thresholding, hierarchical grouping of iso-intensity contours, segmentation of regions and upsampling their boundaries because we have downsampled to the full resolution image, analysis of the segmented images to reject false positives, and classifications of the regions detected. I mentioned one other thing. At the initial stage, you want high sensitivity, even if you allow many false positives. Detect everything that looks like that could possibly be a tumor. But later on, reject all the false positives, or as many false positives as possible. Reject them by applying other criteria. If you miss the tumor at the first stage, that is, if your sensitivity is low, you will not detect it again in the subsequent stages, because the subsequent stages after this are for rejection, not for detection again. So that's an important consideration. The initial step will give us many false positives, and that is fine. The general idea is a mass is denser than the background, breast or wherever, whichever part of the image. A mass means it is denser. A tumor will be denser. And tumor is also active in the sense it is growing and it is spreading. So if you smoothen the image, apply a low-pass filter, all the minor details will be suppressed, and this mass will become like a mountain. And if you were to cut the result into slices based on density, you get iso-intensity contours that are closed loops, where along each contour you have the same pixel value. Like contour maps in elevation. When you have a mountain, you have a flat region and there is a mountain, and the elevation map will show you these contours where the elevation is the same, like maybe here, starting from the ocean, it is 0 and 10 meters and 20 meters and 30 meters and 100 meters and so on. So when you go to the top, there will be a small circle indicating the peak of that mountain. So when there is a mountain or a hill, then there are a number of these iso elevation contours, one inside another, going to the peak. That is the basic idea here too in the detection of masses. But first you have to smoothen the image, filter, low-pass filter, and downsample and create these maps so that minor details like other ligaments, ducts, calcifications, they're all wiped out. You cannot do iso-intensity directly on the original image. It'll be too noisy. So there is a framework for pyramidal decomposition that Naga created. I call him Naga. Mudigonda is what is shown there. That's what I already said. So there is recursive wavelet decomposition and Gaussian smoothing operation, and because you're smoothing, you're getting smoother and smoother images, and it is multi-resolution, and each image is smaller and smaller than the original. Like you may start with a 1024 by 1024 or a 4000 by 4000 image. Next will be 2000 by 2000, 1000 by 1000, 500 by 500, or whatever the step size is. So you get a pyramid of these multi-resolution wavelet filtered smooth images. So it is iterative decimation compared to the full resolution image. So there is a hierarchy of sub-images with progressively decreasing bandwidth and increasing scale. So in each of these, you detect these contours, iso-intensity contours, and map them. So wavelet decomposition divides the frequency spectrum of the original image into its low-pass subband equivalent image, FL, and high-pass equivalent detail image. This is standard wavelet decomposition. And the low-pass subband image at each scale is further smoothed by a 3x3 Gaussian kernel, and the result imaging is stretched to the range of 0 to 60 in pixel value, some limited range. Okay, this shows the wavelet in 1D. This is the simlet at 2 scales. The wavelet looks like that, and this is order 8, order 4, order 8. So here is a part of a mammogram. I show only parts of mammograms. We will show the detection in a full mammogram later. So this is the original mammogram, a small part. The width is 51 millimeters. 1024 by 1024. Sub-image. The full image is 4K by 4K approximately. So these are low-resolution filtered images obtained by wavelet filtering. First level of decomposition, this is 512 by 512 pixels and 100 micrometers per pixel. This is after 2 levels, 256 square, 200 micrometers per pixel. And this is third level of decomposition, 128 pixel square, 400 micrometers per pixel. So with the smoothing and downsampling, and the images are displayed to the same size for the sake of display. Otherwise, a pyramid is shown by getting smaller and smaller images. They are downsampled. But you can display to the same size for convenience here. So these are the masses, the 2 bright regions there. So some of these other details are suppressed and the masses get enhanced in this process. Minor details are suppressed. So now segmentation based on density slicing. The assumption here is that recursive smoothing and decimation operations, as I showed in this picture, result in gradual modulation of intensity information about the local intensity maxima in various isolated regions. So intensity levels are expected to assume either unimodal or bimodal histogram distributions. Minor details are removed and gathered, and the histogram becomes simpler. Now you threshold the image at varying levels of intensity, that is, you cut at multiple levels and get the iso-intensity contours. Let me go to this illustration. So here is sort of a peak in the gray level image. That could be a mass. When you cut at these multiple levels, you get these iso-intensity contours, mutually enclosing, or we can call it concentric. They're not exactly concentric, but one inside another. And that could be called a family, because one is inside another. You would call that a family. There could be other such families, but if a family has only 1 or 2, then you say that's not significant. If there is a significant peak, it must contain a number of such contours, one inside another. Then it is a significant peak that could be a mass or a tumor. There is some modeling here as to what the threshold should be. I'll skip some of these details. So grouping of iso-intensity contours. In the low resolution image, or from the low resolution image, you go to the contour domain. And you get these multiple families of contours at different resolutions. And you want to put them together and get segmented regions. I'll show these pictures now. As you asked, when I skip something, you don't have to read that for the test. I say some of those with reference to the image. It's easier than reading all of that. But you may read all of those if you wish later. But the pictures tell the story. So here is a part of a mammogram that I showed with the two dense regions. There is a third dense region here. So these are the contours, the red lines. The blue lines are the reference, are the contours detected as representations of some dense objects. So if you look at this, there are, I don't know how many, maybe 3 or 4 contours there, one inside another. It is not a significant object. If you were to take this contour, there are more contours inside that blue contour. So the blue contour here is detected as a significant family, the outermost contour of a family of contours within which there are a certain number of contours. I don't remember, 5 or 6 or some number. And that also passed the test. So I can zoom this. So you have 1, 2, 3, 4. Maybe we'll put a limit of 4. You could change that. So this passed the test. The fifth, 1, 2, 3, fourth one, that is the contour. The others are going away. They are breaking, you see there. So the other contours are not enclosing it completely. You see here, there are multiple, 1, 2, 3, 4, and 5, and 6, and 7. That is the 7th one. So in this manner, you detect the outermost contour of a family containing a certain minimum number of pre-specified minimum number of contours. Then it is a family. This is not a family. 1, 2, 3 is not a family. These are rejected. This is something that is not meeting those criteria. So this is the result. This also passed the test. The black contours are the contours drawn by the radiologist independently. So we have 2 false positives. Yeah, the black contours drawn by the radiologist. That's a histogram, let's not worry about that. This is a malignant tumor. I'm showing only that part. And you see so many contours inside the blue contour. I'm only showing that part. So in the case of a tumor, it works well. And that was the black line is the contour drawn by the radiologist, and the white line is the contour obtained by our method. That spicule was missed, so you don't get everything. So benign versus malignant pattern classification was carried out using texture features, using Haralick's methods. At that time, we only had 29 masses, 19 benign and 10 malignant, and got an average classification ratio of 0.8. Entropy, second moment, second difference moment, and correlation, those were the shortlisted features from the 14 Haralick's methods, Haralick features. Using adaptive ribbons like I showed around the boundary of the tumor, not the whole region. Now, to detect masses in full mammograms, we need to do a little more. What I showed was how it works on segments containing masses. First, we do detection of breast boundary. You have seen that. So that's the image. Now, this tumor is fairly large. Anyone can see it. But I'll show other examples. The breast boundary, and these are isointensity contours. Now, around this mass or tumor, it looks like a thick line, but there are multiple contours there. So if you zoom in, there are multiple contours. It's not a thick line. I'll remove some of this. I want to go to, we did using texture flow field. This was something that Naga added to reject false positives. We found that most of the false positives were caused by overlapping fibroglandular tissue or fibroglandular tissue of high density. Masses were detected, but we were getting these other false positives, like these. But look at the original image, and those are fibroglandular tissue, and here they are intersecting or overlapping. When they overlap or intersect, we have regions of high density. So those were getting detected and passing some of these criteria. You don't have the family of contours for all of these, but some of them still passed. But in analyzing these false positives with the radiologists, we found most of these were strongly oriented fibroglandular tissues. And we wanted to distinguish between the masses and tumors that are true regions of interest and the false detections due to fibroglandular tissues. Rao and Shunk proposed to characterize flow-like information using what they call intrinsic orientation angle and coherence. The orientation is computed at every pixel using gradients, but a 2D Gaussian smoothing filter is applied. We have seen Gaussian filters of that kind. So the impulse response of the gradient of Gaussian filter, you take the gradient and include angle, gradient of that, and that is the gradient of Gaussian filter. So there is a gradient computed with smoothing and orientation. So at each point in the image, the filter HXY, when you convolve, it yields maximal response in the orientation theta that is perpendicular to the orientation of the underlying texture or angle of anisotropy. So what we need is this angle of anisotropy. And how do you characterize that? You get the gradient magnitude and you get the gradient angle, as you have seen before, but now we are using Gaussian, gradient of Gaussian, so to include some smoothing for noise control. Theta Mn is just the tan inverse of the y over x. We have seen all of that. So the projection of this vector, Gmn, with its angle theta Mn to some other angle theta pq is this. So you want to ask, how does it project to other angles? So there is some dominant angle, GPQ, and there is a neighborhood pixel Mn. It has Gmn. What is that projected to this vector, which is that? So you want to ask what is common between that and this in terms of orientation and strength. That is texture flow analysis. So the sum of squares of the projections, S equal to sum of G square Mn cos square theta Mn minus theta capital theta, that is the reference orientation. So you do this for all the pixels in a certain neighborhood as shown in that block, 5 by 5. Take the derivative of that and set it to 0 and solve, go through this process. And the estimated orientation angle of flow at that point is this quantity. The gradient vector is perpendicular to the direction of flow. So this is texture flow analysis. Now note that there is another method called optical flow where you are dealing with functions of time. So here it is, nothing is flowing, it's a static image, but how does texture at a point compare to a reference point in terms of gradient orientation, or orientation flow we can call it. Some parameters, let's not worry about that. Now, what is coherence? Coherence is comparing the gradient at one pixel with its neighbors. GPQ is the point PQ, the gradient. GMN, the gradient at the neighboring pixels in the 5 by 5 neighborhood as shown earlier. Theta Mn is the angle at that location. Minus psi PQ is the angle at this point. So this is the projection, this is the normalization. So this is a measure of coherence. If all of these are in the same direction, that cos theta minus psi will be 0. So you will get a high projection. If there are other angles, the projection will be reduced. So they don't agree in orientation. And if the gradient magnitude is high, and here is also high, you get a large value. So if the gradient is high and the angles agree, then you get a large value averaged over a 5 by 5 neighborhood. This is coherence. Ligaments or structures like this, in this orientation will be highly coherent. They have the same orientation and similar gradient, angle and magnitude. So along that axis of the ligament, you will get a large value. Most of our false positives were caused by these ligaments. So we wanted to identify structures that are coherent and get rid of them. Tumors and masses go all the way around. There is no coherence in them. There is no preferred orientation. So these are the false positives. And these are the lines showing the intrinsic angle, the white lines. So if you were to, this was done for the whole image. So if you see around the tumor, the angles go all the way around the edge of the tumor. Here the angles are going in various directions. But if you come to ligaments, these are the false positives that were bothering us. You see the orientation is similar along, not this one maybe, well there is some there. Look at something longer, the angles are the same. So when you analyze those regions, we can recognize them as coherent structures, and even if their density is high, even if we got a high response from the previous method, which is why these were marked initially, false positives, but we will reject them at this stage. There is one here which is inside the pectoral muscle, and we were told that could possibly be a lymph node affected by cancer, which is this tumor. And look at the orientation along the pectoral muscle. These lines go that way, the orientation of the gradient. And look also, in general, the tissues in the breast converge towards the nipple. There is an orientation pattern, there is an overall convergence. That is the oriented pattern that is present in the breast. The ducts, the ligaments, the milk ducts converge towards the nipple, of course, but all the supporting structures also converge that way. And that is shown by this intrinsic angle map. And when there is a tumor, that is disturbed. So that is another method that could help in the detection of tumors. If there is such disturbance in the overall converging pattern of the breast tissues towards the nipple, then there is a local disturbance. We have used that to detect architectural distortion. You will see that later. I'll go a little more. We are almost done. We'll finish this and then stop. This is the intrinsic coherence image where you see large coherence along the ligaments. Around the boundary we get a little bit, but not inside. You have to scale this and zoom it. You will see that. We then computed the features in adaptive ribbons. We have already seen that. The width of the ribbon was defined in proportion to the area of the region and area of a circle containing the region weighted by RC, the radius of the bounding circle. The ribbon size was about 8 millimeters or 40 pixels. So these are the ribbons to compute texture and other features, including false positives. Contrast, coherence, ratio, these are the features computed. Entropy of orientation estimates of the spicules of the margins. Variance of coherence weighted angle estimates. These are all measures of variance alpha I minus mu h, where alpha are the normalized values of the histogram and mu h are the average value of those. So benign versus malignant classification is what we were interested in. So we got some results. Let me just go to the results here. So in this particular case, the tumor was the only one left at the end. All these other false positives were rejected using the additional features I mentioned. This is, Dr. Desertel said this could possibly be a lymph node affected by cancer, but we were not sure of that. So we can say one false positive. This is another mammogram where there is a very small mass. The radius is 5 millimeters. And the initial stage was this. It was detected with so many false positives. And after pattern classification and rejection of false positives, we got that with one false positive. Benign versus malignant classification, the overall accuracy was 0.79, which is not very high. The database was small. So I won't claim anything big about that, but at that time that was substantial. So that paper was published in the Transactions on Medical Imaging. We only had 32 cases, so that's not a very reliable result, but it was an important method and result at that time. So what I would like you to note here is that masses and tumors may be detected by smoothing the image such that they appear as mountains or hills or some large objects with substantial height compared to the background. And then if you do slicing, density slicing, you get these families of contours which will help in separating substantial objects versus insubstantial objects. Still, there will be false positives. You have to analyze what is the nature of the false positives in your application. And in fact, as I said, first, you must allow for false positives in order to have high sensitivity at the initial stage. And then reject. You saw there were so many false positives, and most of them were rejected, at least in the two examples. Our sensitivity was, it's somewhere there. We got about 82% or so sensitivity with 2 point some false positives per image, which was reasonable at that time. So analyze the nature of the false positives. In this case, they were oriented fibroglandular tissues. And because they were oriented, we computed the measure of coherence, which characterizes patterns with a preferred orientation, and the coherence is computed with reference to that orientation. Then we could reject those. And the masses, being incoherent with reference to that measure, remained, and they were not rejected. These numbers are not important right now. We are talking about the methodology. Okay, we have crossed 12:30. Do you have any questions before we break for lunch?
I want to see the first example. In slides. I want to see the first example in the slide. No.
The one with the big mass?
Yeah. This one. So isn't it near the pectoral muscle?
It is near, the pectoral muscle is here. This is inside the pectoral muscle. The tumor is in the breast portion. There is a little bit of separation, yeah.
So the radiologist said that it would be a problem in the lymph node. So what is the classification that is said then? Why can't it be a tumor as well?
Which one? This one?
Yeah.
That's not the breast. That's the pectoral muscle behind the breast. So it could be, it is typically a lymph node that could appear there, and if that is affected, it'll show up as higher density. So it wouldn't be called a tumor, it is a side effect of the tumor. And it is not in the breast, technically speaking or anatomically speaking there. So the breast tumor is this one. The other is some other dense region in a, you can say, different part of the body, but it is just a muscle near the breast. But it's the pectoral muscle. It could be a secondary tumor if you want to call it so. But I was told by Dr. Desatil that it could be a lymph node that's been affected and is showing up with higher density in the pectoral muscle. That is what the radiologist told us. So it's a difference in terminology. In the lung, perhaps you would say, if there is another region like that, you would say it is a secondary tumor. So here it's not called a tumor. And we didn't want to call it a false positive because it has some relevance in diagnosis. But if you just look at detection of tumor, that is a false positive. Okay? All right, let's break for lunch. We'll come at 1:40, 1 hour from now, 1:40, right? Doctor?
Links later about maybe like
All right, I hope you had a nice lunch with the kadale bele paisam. So let's look at another important sign of manifestation of breast cancer known as bilateral asymmetry. We have seen two signs of breast cancer: one, calcifications; two, masses. The third, in the order of importance and in terms of occurrence and how often such signs are met, asymmetry is another. Now, asymmetry is not in one mammogram, but comparing the mammogram of the left breast with that of the right breast in the same view. Craniocaudal CC of one versus CC of the other, or MLO of one versus MLO of the other. So you need two views of two breasts to compare. Normally, the two breasts should have similar appearance, not identical. There'll be some small variations, normal anatomical variations, and also small variations due to the projection. The breasts are compressed differently and integrated differently. So there will be differences. But if there are large-scale differences or large or substantial differences, then it is known as asymmetry. And there is also the notion of focal asymmetry. That is asymmetry in a small area of the breast versus global asymmetry, where the entire breast appears different. But how do you compare? You don't want pixel by pixel comparison. Pixel by pixel, most images have high correlation. We want to compare structures that are present, and so we need some pre-processing steps to extract the structure. The pectoral muscle is not important, and all the details outside the breast boundary are not important. So we have to perform segmentation, remove everything outside the breast boundary, remove the pectoral muscle in the case of MLO views. And also within the breast, there are different types of tissues. And you may want to remove fatty tissues or just fat and concentrate only on the fibroglandular disc, as it is known. So we will look at some of these details. This work was part of the PhD project of Ricardo Ferrari from Brazil, who did his part of his PhD thesis with me. So this is based on directional analysis using Gabor wavelets to analyze the global disturbance between the left and right mammograms. What we would expect is normally symmetrical flow of mammary structures between the left and right, but if there is some disturbance, that is, they don't match, then we say there is asymmetry. It was focused on the fibroglandular disc of the mammograms, segmented in pre-processing steps. So what is the fibroglandular disc? It is an anatomical region of the breast characterized by dense tissues, ligaments, vessels, and ducts. The fatty portion is removed. Just close to the skin surface, there will be some fat, and that doesn't contribute to structural information, and certainly no directional information. So we focused on the directional content and not on density, and later on we added density and overall shape. So initially we focused only on the directional distribution of oriented fibroglandular tissue. So segmentation of the fibroglandular disc is an important stage in the detection of asymmetry. And it's been shown that breast cancer occurs most frequently in the upper and outer quadrant of the breast, and it is associated more with glandular than fatty tissues. So that's why we need to concentrate on this part. So first we detect the breast boundary and the pectoral muscle. You have seen those methods, and they are removed. The fibroglandular disc contains different types of tissues. It's not one thing. And for that, we made use of a breast density model. The parameters of the model are estimated by using the expectation maximization algorithm. EM is expectation maximization, and the minimum description length, or MDL principle. The pectoral muscle is detected and removed, but the density of that is used as reference to detect dense fibroglandular tissue. So first, there is the mixture model, in particular Gaussian mixture model of breast density. So we get the histogram of the breast part of the mammogram, and we need to indicate how many categories are of interest, how many Gaussians do you want in this mixture model. And it could be 3 or 4, it depends. You could say it depends from 2, varies from 2 to 4, but it varies from one image to another. So what are the 4 types? Uncompressed fatty tissues that are localized in the periphery of the breast. Fatty tissues composed of fatty tissues that are localized next to the uncompressed fatty tissues and surround the denser areas a little inside compared to the skin boundary. Non-uniform density tissues, they are high density portions of the fibroglandular disc extending close to the chest wall, and then high density tissues in the fibroglandular disc. So these are the 4 types of tissues, and uncompressed fatty tissues and fatty may not be of interest, but they will be there. So when you have a mixture, suppose there are k types, px given theta I bar, that is the probability density of one of those, and there is a weighting factor wi. The histogram of the image that we're dealing with, or the part of the image, is the sum of those PDFs. The sum of these weights is equal to 1. Now px given theta I is in this case Gaussian. Theta is a vector mu sigma of that component. You may have 2, 3, or 4 components. So mean and standard deviation. And theta bar represents this capital theta bar, the collection of all the parameters, W1, W2, so on, WK, theta 1, so on, theta k. All of them form the parameters that you want to find in fitting this Gaussian mixture model to the histogram of the given image. K is the number of Gaussian kernels or tissue categories, 2 to 4. So this is just the Gaussian. Now here we are using only density, and there are only 2 parameters, mu and sigma, of that density histogram. But if you want to bring other features, in general, you may want to use other features like texture. Then you have a multivariate Gaussian. You could put, instead of x, you have x, y, z, and so on, or x1, x2, x3, more parameters. You could, if you wish, but we haven't done that. We have used only the gray level values. So the Bayesian assumption is made that the PDF associated with the pixel is independent of that of other pixels in a given class of tissue and independent of position in the image, and estimation of parameters is performed using the expectation maximization algorithm, which is an iterative procedure that maximizes a log likelihood of the parameters for the model of a data set representing a PDF. So you're given the histogram of PDF, and you have to find those parameters W, mu, sigma, as many as the number of components. So in the first step, the expectation step, the current set of parameters is used to compute the model, and then in the next step, the M step, or the maximization step, then the parameters are re-evaluated with respect to the new data distribution by maximizing the log likelihood given by this log of the likelihood of theta bar given this function, the data sample rather, given this observation. So n is the number of pixels, and this represents the data sample. So given that, you want to maximize the expectation, and it is iterated until the values of this log function between 2 consecutive steps don't differ much. So there is convergence or some limit on the number of cycles, such as 200. So how do you start the process? You need to put some initialization value. So you say mu I is new, some random value in the range defined by the minimum and maximum gray levels present in the effective area of the breast. So you don't give it any random value, but depending on what is present in the image. And WI is 1 over K, that is, they're all uniformly distributed, all equal weights. The variance of each Gaussian was initialized to the nearest distance to the other Gaussian kernels. So the procedure is then iterated, and then you find the parameters. How do you select the number K? How many components do we have in this case on hand? So then this log likelihood minus nk over 2 log k. So here we have the MDL principle to select the number k of the Gaussian kernels or the mixture model entries. Nk is k2d plus 1. D equal to 1 is the dimension of the feature space. K is the number of Gaussian kernels. So now we want to delimit the fibroglandular disc. So here is a mammogram, the pectoral muscle edge and the breast boundary detected using the methods we have seen so far. And that is the effective area. And now we have the image histogram is this dashed dot. There are too many curves here. That is the histogram of the image. And then there are 4 Gaussians, 1, 2, 3, 4. And this is uncompressed fat. This is fat. This is non-uniform density. This is high density related to the gray level value. Fat is low, dark in appearance in the mammogram, low attenuation coefficient for X-rays. So when you add them up, you get the mixture summation, which is this thin line. It is fairly close to the original histogram. Small deviations, of course, exist because you're using only 4 components. So now we have 4 components with their relative weights, and you know the mu and sigma of these Gaussians. So you can say the fibroglandular disc is made up of these components. Now you can, using the statistics of these model Gaussians we have determined, we can break the image into parts by thresholding. So this is the core area. These are the 4 densities: fatty, compressed fatty, mixed, dense. The 4 categories from the Gaussians. Now you apply back to the original image that was segmented, pectoral muscle removed, breast boundary. So within the breast boundary now we have these, and the densest part is this, which you call the fibroglandular disc. The density of the pectoral muscle can be used as a reference in the interpretation of these densities. The pixel values are normalized 0 to 255. It's not like CT Hounsfield unit numbers. So we don't know what 0 is or 10 is, what 200 represents. So use the pectoral muscle in the case of mediolateral oblique, MLO views. In the case of CC views, you don't have such a reference, but from the same breast, if you have the MLO, you can use that as reference. So regions of similar brightness or density will most likely correspond to the fibroglandular disc. So if a K-level cluster was classified as the fibroglandular region, if mu K is greater than mu P minus sigma P, where these are the mean and standard deviation of the pectoral muscle region. Mu K is the mean gray level of the cluster K from the effective region of the breast. So using the pectoral muscle as a reference, well, in any case, you take the densest portion. I think we went through all of this. This is simply listing of that. So another example. That's the image. Pectoral muscle edge and breast boundary, all of these other things are removed. And here you have the dot dash line is the true histogram, and you only have 3 Gaussians in this case. So this is fat, this is uncompressed, this is uncompressed fat, this is fat, and this is high density. Of the 3, that is the highest density. When you add them up, you get this solid line, which is fairly close to the original histogram. So break the effective area into parts and take the densest part, that's the fibroglandular disc. Note that there are parts that have been removed within also, so it is not a compact region. It's called a disc, but in this method we don't get a compact region. There are parts that are missing, in the sense they're not included in this fibroglandular disc, and there could be some artifacts like that. If you wish, you can process this further and remove such bits and pieces. So these were evaluated in consultation with radiologists. I won't go through the details of evaluation. Let's assume that the results are good enough for further analysis. In Riccardo Ferrari's work, we used a bank of Gabor filters and the KLT, Carhon-Liouville transform, which is related to the PCA, or principal component analysis, similar, to extract the strong components and reject weak components or uncorrelated noisy data. So again, Gabor filters, you have seen this before, so I don't have to go through that again. Gaussian and complex exponential modulation included in the exponential frequency of W. And rotation, scaling and rotation. So Gabor filters now, another illustration. In the space domain, the impulse response is an image. So the Gabor filter has a positive main lobe, negative side lobes, positive again, negative again, and so on, decaying. But it is oblong. It is long in this direction, short in the other. So this will detect horizontally oriented thick patterns. So this is rotated. It will detect positive contrast, bright patterns at that angle, thin bright patterns at this angle, very thin patterns at that angle. So the parameters of the Gabor filters need to be determined in accordance with the characteristics of the tissues or patterns you want to detect. How thick and thin are they? How many scales do you need? What is the ratio, aspect ratio? How long does a line go in a given direction before it curves? These are not straight lines. These curve, but for a short length, you can assume it to be straight. How long is that? Is it very short or is it long? So depending on that, you have to adjust this parameter. If it is very short, use short, small Gabor filters. If they are thick, this. If they are long, use this. Short, use those. So that is scaling and rotation. We saw this also before, so I'll skip. This is the frequency domain representation, where W is the shift in the U-axis, and sigma U, sigma V are inversely related to sigma X, sigma Y. We saw some of these equations earlier, and you will see it once more. So this is how the frequency space is broken by the Gaussians that are the Fourier transforms of the Gaussian in the Gabor filter formulation, the wavelet formulation. So for different angle rotation, you get these, and scale factors. Very low frequency, medium frequency, high frequency. So we used 4 scales, 1, 2, 3, 4, and 12 angle bands. And we use all of them. For the pectoral muscle, we used only these. Now we use all of them. 48 filters. If we use different aspect ratio, you get this. Now these are, each one of them is a Gaussian. This is a section through the Gaussian at half the gain. So it will look like an ellipse. So what is the range of frequencies which this filter passes with gain more than half? Amplitude gain. Power gain, that is more than half power. This will pass these other components with lower gain. The gain will reduce. I showed some of these parameters earlier. Some of these are being repeated. I'll skip some of these details. We only use the even part of the Gabor filter. It was shown as a complex function. The fibroglandular tissues are brighter than the background, so you only need the cosine function. Cos theta plus j sine theta, you only need the cosine. The exponential formulation is for the general case. If you have both bright patterns and dark patterns to detect, then you must use both. You can do them separately and combine later. Cosine first and then sine, and detect bright and dark patterns. There is multi-scale analysis. We said we have 4 scales. And for each scale, for a given angle, we get a stack of 4 images. And then we have these pixels, x1, x2, x3, x4, form a vector for the 4 images for a given angle over the 4 scales. And then you need to find out which value you want to take. So for that, we used the KLT, or principal component analysis. So the eigenvectors of the covariance matrix were computed and arranged in the matrix A in descending order over the corresponding eigenvalues. And the first n principal components corresponding to 95% of the total variance were selected. And they were used to represent the oriented components at each specific orientation. So this is the Karhunen-Loew transform, KLT, or PCA, principal component analysis. They are similar in formulation, depending upon which way you want to view it. And the principal components were computed as y equal to ax minus mu, where x are these vectors for each pixel. And this is done for every pixel and over 4 scales, and then for every angle. So for every angle, and finally you get one set of values from here. And then Otsu's threshold was applied, and then you get a binarized image. Phase and magnitude images were obtained, indicating local orientation and intensity by vector summation of the K filtered images. There are 12 directional components. So what is the direction at a pixel? It could be in between those 12 values. So you perform vector summation. I mentioned that vector summation earlier. When you have multiple directional components, the actual direction could be somewhere in between them. This is what I have already described so far. So here is a pair of images, left and right, MLO images. You can say MLO because of the presence of the fibroglandular disc there. And these are the enlarged fibroglandular disc for the left and right. So the pectoral muscle has been outlined here in black, the breast boundary in white, automatically detected. Sometimes we try to avoid automatic. Previously, automation was seen to be something good. At IISc, next to electrical engineering, we had School of Automation, and I was really thrilled by that, School of Automation. And automation was seen to be good at that time, And then came robotics, and then people got a bit afraid that robots will replace us. Now there is a fear that AI will replace us. But that hasn't happened, and this will not happen. But in diagnostic application, one has to be a little careful. So instead of saying automation, you may want to say computer-assisted, computer-aided. You don't want any automated surgical procedures, some robot coming and ripping my heart out. No. There is robotic surgery, but it is controlled by a surgeon. The robotic arm is controlled by a human being, whether right there or somewhere else. So, yes, you can accept it to some extent, but when you express this and tell somebody, I have this automated diagnosis, then there will be some concern. If you say computer-assisted, fine. It's like we use the calculator, but I'm the engineer, not the calculator. So I'm using the calculator as a tool, or even a ruler as a tool. That doesn't determine the final product. The computer doesn't determine my lecture. I'm giving the lecture. I'm using the computer as a tool. Similarly, the physician can use it. But if you say automated, there could be some negative connotation. And that's why I also avoid the terminology associated with machine learning and artificial intelligence. Anything artificial, one would be concerned, especially in medicine. I want a real doctor who has passed all the exams properly, not paying and doing some wrong things. So I want a real doctor, not artificial. Similarly, automation, one needs to be careful. When you want to explain this to patients. So these are the fibroglandular discs for the left and right, sort of similar. They're not identical. This is a normal case. This is a case with architectural distortion causing asymmetry. You can see that the density distribution is a little different. Look at this dense area and compare there. And look at this and compare there. There are differences. The fibroglandular discs. If you were to look at this area and compare the corresponding area, you see other things. There appears to be some calcification there, but that is not important in the analysis of asymmetry. Asymmetry could also be related to the placement of ducts and vessels and the enhanced presence of vessels and ducts in one and not in the other breast. So it is not simply arrangement of tissues, fibroglandular tissue, but also ducts and blood vessels in general. So this is a case of asymmetry. So these are the directional components at 4 scales. Large scale, small scale, smaller and smaller. The finer scale, there is nothing. So in such a case, there is no point in using 4 components. This has nothing. So through PCA, perhaps these two are rejected. The eigenvalues are 10.8, 0.89. So right away, the second one is so small. Lambda 3 is 0.09, lambda 4 is 0.01. So these two will quite likely be rejected. But that depends on your threshold. So put them all together, you get the magnitude response. Let me just check. Both are magnitude for the normal case. Now there are some differences. They are not identical. But here is a Rose diagram for these two. Most of the energy or fiber covered area is here and there. The others are small. So there is some similarity. They are similar, not identical. Take the distance between them, Euclidean distance. Compared to others, it will be small. If you want to take a close look, here you will see differences. But look at the Rose diagram, perhaps they agree quite well. This is an asymmetry case. More substantial differences visually. And in the rows diagram, you see larger differences. Large here, not so large here. And large there and not so large here. So in this manner, we reduce the information from the image to a rows diagram like this. And then take the distance between these as vectors. So feature extraction. The entropy H of each one, the first moment M1 as we have seen before, second moment of variance M2 of the rows diagram given by the difference. Now you can subtract the rows diagrams. Later on we did another alignment with reference to the principal axis of the image. In this we are not rotating the images, but it is possible that one image is slightly rotated with respect to the other in image acquisition, digitization and so on. So that could be taken into account. Here we are directly subtracting the rows diagrams. We get a difference rows diagram, and then from that we get the entropy first moment, second moment given by the difference of the rows diagram, that is the difference between the two left and right rows diagrams. So we used various pattern classification methods. Let's not worry about that. We got sensitivity, specificity, average accuracy in the 70s, mid-70s range. Not the greatest, but we got better results later by including some further features. So we revised this method. The rows diagrams of the left and right mammograms were aligned such that their mean angles corresponded to the straight line perpendicular to the pectoral muscle, and then subtracted. So the pectoral muscle edge is taken as a reference, and take the perpendicular to that and align the rows diagrams with reference to that. If the two perpendiculars don't match in the image, then one rows diagram is to be matched. Or you can say we align the rows diagrams to that, both of them. So in addition to the three features I mentioned, entropy, first and second moments, the dominant orientation theta r and circular variance s squared theta were computed. So you get xr as ri cos theta I summed over n, yr is ri sin theta, theta r is yr over xr, and the variance is this. Ra is a normalized value, and theta is the central angle of the ith angle band of the difference rows diagram, left minus right. So these are additional features. I already mentioned that. And then we computed eccentricity of the fibroglandular disc by taking the moments, second order moments, and normalizing them in this manner. So this is related to shape variation in the segmented fibroglandular disc of the left and right breast. So again you subtract the two. And a stretch parameter was computed. So these are very basic shape analysis methods for the fibroglandular disc. We don't want fine shape analysis of shape roughness, but general alignment of the two. So we had a number of features. So feature selection was performed by principal component analysis again, and exhaustive combination techniques, and components with 98% of the total variance were used in the classification step. And classification was performed using linear and quadratic Bayesian classifiers with the leave one out method. Those are classifier methods. We won't discuss the detail in this course. In all of our projects, our aim is to design appropriate features. If you design very specific features for the application, and if you have taken the important discriminating aspects between the categories into account, then the classifier could be a very simple linear or quadratic discriminant classifier. Bayesian if you want, or logistic regression, very basic classifiers. No fancy big neural network, and you can do radial basis functions, neural network, and so on. But the more complex the method that you use, the higher the probability of catching on to the intricate details of the data set and being data dependent. So if you use just a basic classifier like linear discriminant analysis, just find a boundary or quadratic, then it is unlikely that your classifier will be data dependent. So we got slightly better accuracy going to 84, 82, 86% using those two features, theta, M1, M2, and H. We added the morphometric measures, and if you use only the morphometric measures, the accuracy is only 71.1%. So the angular information is important. So asymmetry depends on the angular distribution of the fibroglandular tissues. The shape parameters of the fibroglandular tissue they contribute a little bit, but they're not the leading factors in determining asymmetry. Okay?
Observation here is like, all these methods, we were included like the geometry of the feature and many other things, rather than, and that leads to a very simple classifier, like as you just told, like. But in contrast to the deep learning kind of a setup where the feature becomes kind of an abstract number, so the classifier becomes the more sophisticated. Like.
Yes. Yes, the classifier becomes more sophisticated if you don't extract features and just dump the raw data. It'll learn somehow. One could say radiologists also learn by looking at hundreds of these pictures. Nobody drew these boundaries or computed these features. They did it by visual analysis. So deep learning experts will say, they did it and you will do it that way. Why not a computer? You looked at 1,000 or hundreds of these images and you learned how to detect this and how to detect that. You never computed any objective parameter. You didn't segment the image, you just looked at them. So they say, well, dump the million pixels or 10 million pixels or how many ever pixels you have and let it learn. But for that you need a huge database. In such cases, our data sets are small. And because they are related to features that radiologists have observed over decades or years of their own experience, their experience has come in here, and we are just capturing that experience in terms of these features or attributes. So there is more value in this than simply looking at the picture. One, the observation of the radiologist. Two, the way we have learned signal and image processing, which has advanced a lot over the past 40 years. When we started learning DSP, it was only the book of Oppenheim and Schaefer, and we started learning image processing. It was Gonzalez and Wintz, the first edition, only this much. The book was this much. Now it is that much, and it's not enough. And my book will be that much, 1,300 pages, and there is plenty more. They will say, oh, you left this out, you only have mammograms. Well, that's what I have worked on. Now we are adding retinal images and other images, and you keep adding, it will become a whole lot. But for each one of them, you need the domain expertise to be brought in. What works here may not work there. So if you simply dump mammograms and retinal images and CT images and MR images, it doesn't work. It's a brute force method. Whereas these so-called handcrafted features are specific to each one of these. So what do? Well, you want to detect architectural distortion or asymmetry. We have to detect all of them. It's not one. Breast cancer can appear like this or like that or like that or like that. All of these have been observed and recorded by radiologists in the BIRADS manual and so on. So we take those and design parameters accordingly. So your design may be better than mine, yours may be better or should be better. If you want a PhD, you should do better than what has been done. So eventually it will get better and better. So we start somewhere and it has to improve.
More human feeling in this kind of a thing, and computers these days, deep learning is more of a numbers, where computer can understand only numbers.
Yeah. No, but the argument I've heard from deep learning proponents is that the various stages of convolution in the convolution neural network, they do some feature extraction, but they can't tell what is being done. They say, yeah, we can design, and by providing appropriate examples, it will learn. But here, we have learned it and we are putting it. But my understanding may be limited, and your understanding could be better. And having seen this, you should be able to do something better. And it will improve that way.
So was there any instance where you were talking to engineers who were working on acquiring these images?
Image acquisition is not under our control. The Alberta Cancer Board has set up the screening program for breast cancer. And they're medical physicists. Engineers don't do that. Medical physicists will be involved in the design of imaging devices, image capture devices, dose requirements, and all of that. And that is set up by the screening program, and I cannot intervene or interfere. I cannot even touch those images. I cannot go through those patients' files. As I said, to digitize those, a member of the screening program came to our lab and she scanned and she took all of them back in the evening and put them back in the screening program office. So I cannot go and do anything with that acquisition protocol. My job is only after the image has been taken. Now, if you're in a different research setting, you are working in a hospital, then you can go and change that. Screening programs are different. Diagnostic, different. In a hospital, if you're a member of that group, then yes, you can go and do that. But typically that requires medical physics training and not electrical engineering. Yeah?
And one question that Gaboo sunflower type of affairs are. Suppose there one vowel is here, another is here. There's a patch in between. A frequency component.
No, there is no. It looks at the current mammogram. Mammograms from the 2 previous sessions are displayed. That's the protocol. So they look at the previous one. If they see something, a tumor here, they look at the previous one and say, was there something I missed? Was there something at all that should have been detected? So there is a quality control analysis there, check. And previous screening mammograms were seen to have some signs, minimal signs. This is after the fact. I detected the tumor, so I see, and oh, there is something. But without this, at that time, those were seen to be perhaps not suspicious. Or if there is suspicion, they would have said, come back in 6 months, or go for additional tests. So there are many studies like that. So how do you detect speculated lesions and distortion? So the breast contains several piecewise linear structures we have seen, ligaments, ducts, and blood vessels. The presence of architectural distortion is expected to change the normal oriented texture of the breast. Fabio Iris from Brazil, he did his PhD with me, and he developed a slightly different formulation of Gabor filters and phase portrait analysis. Gabor filters is just the starting point. So here is an image from the MAIAS database. There is distortion here, but it's very hard to see. It's a dense region. There are a few spicules radiating. The rest of the breast, you see this fairly ordered structure. As I said, they should all converge towards the nipple, somewhere there. But here you will see some tissues going some other way. That is distortion. Instead of going this way, the tissues are going that way, are sort of pointing in different ways. So if you zoom in, it's a little hard to see. You may see some strands of tissue going in other directions. But that's what the radiologist is trained to catch. We may not be able to recognize such patterns, especially in the original image. You will see later on that it becomes easier. So we use Gabor filters first, and then phase portraits. Now, phase portraits have been proposed by other researchers, where you have two differentiable functions of time, pt and qt, and take their derivatives and functions of those. So given initial conditions P0 and Q0, the solution to PT QT is viewed as a parametric trajectory of a hypothetical particle at P0, Q0 at time 0, and then it moves with some velocity P dot Q dot in that PQ plane. So the PQ plane is called the phase plane, and the path traced by this hypothetical particle moving is called the streamline. And the phase portrait is a graph of the possible streamlines in the phase plane depending upon that differential equation. A fixed point in the phase plane is where this velocity is 0. P dot derivatives are 0. P dot and Q dot are 0. So in this equation, we have a first order differential equation. P dot Q dot is A times PT QT plus B. A is a 2 by 2 matrix, B is 2 by 1. So we have 4 plus 2, 6 parameters. In the linear case, there are 3 possibilities for the phase portraits: node, saddle, and spiral. The center of the phase portrait is given by the fixed point. So if you set that to 0, P naught Q naught, and that will be minus A inverse B. The problem here is, given this derivative information, you want to find A and B. Those are the model parameters through some optimization procedure. Or given the PT QT, you find the A and B. So solving yields a linear combination of complex exponentials for PT and QT, whose exponents are given by the eigenvalues of A and the time variable T. So let me go there and show the picture. So a node is the case when the eigenvalues of that matrix A are real and of the same sign, and then there is a diverging pattern. These streamlines appear to go away from a fixed point or the origin or point of reference. When the eigenvalues are real of opposite sign, you get saddle, where you have this kind of a pattern. The streamlines are shown here. This is, at every pixel there is an orientation showing which way the particle would go. In the case of complex eigenvalues, you have a spiral. Now, in an image, there is no movement, there is nothing moving. So the direction is associated with direction of the fibroglandular tissue or whatever pattern you detect. And all of this is in a stationary image, fixed image. Here these are functions of time. So we have to now switch and say these are not functions of time anymore, but these are patterns in the image where the direction of flow P dot T, Q dot T will be interpreted or switched to the orientation patterns. And in the case of architectural distortion, we expect a node. Multiple spicules. These are like spicules. Lines going at various angles with a focal point. So a node is what is expected at the focal point of architectural distortion. We don't care about the other two. So by using phase portraits, we want to detect nodes that correspond to possibly multiple spicules coming out from a single point. But also it could be multiple ligaments, ducts, vessels that are overlapping and appear to intersect at one point in a mammogram due to projection. That is also possible. So Fabio used this for his or developed his PhD thesis based on these concepts. The basic Gabor filter is the same, Gaussian, but we only use cosine. So it is a bit simpler to interpret now, a Gaussian modulated by a sinusoid. Previously, we had the J2 pi W put inside the exponential. Here it is shown separately. A set of 180 kernels was used with angles spaced equally, minus pi over 2 to plus pi over 2. It's getting tired. The projector is getting tired of my talk. So a few design considerations were put in. These are different from what you have seen for the other Gabor filters. So for this application, we said we want a line detector. We want the Gabor filter to detect lines of varying thickness and varying orientation and possibly varying length before the curvilinear structure changes orientation. So let tau be the thickness of the line detector. The parameters sigma x and f naught of the Gabor filter are related or are conceived as follows. The amplitude of the exponential term in that equation, the Gaussian term, is reduced to 1/2 of its maximum at x equal to tau over 2 and y equal to 0. So sigma x is tau divided by this scaling factor 2 square root 2 log 2. The cosine term has a period of tau, therefore f naught is 1 over tau. So we relate the modulating function period to the width of the line pattern we want to detect. The value of sigma y is sigma y equal to L times sigma x, where L determines the elongation or the oblong nature of the line pattern we want to detect. How long will a fiber be before it turns or changes direction? These are not straight lines. So, depending on the resolution of the image, we used a resolution of 200 micrometers. The large images were downsampled for the detection of architectural distortion. We're using fibroglandular tissues. We're not detecting microcalcifications. So we don't need 50 micrometer resolution. So 0.8 millimeter resolution at a pixel size, or this is tau equal to 4 means 0.8 millimeter at a pixel size of 200 micrometers, and L equal to 8 were used. So these are a few Gabor filters similar to what I showed earlier. This is a Gabor filter at some parameters. The Fourier transform is this. This is the Gaussian. As I was telling you earlier, each one is a Gaussian, but it's decaying slowly. You can see all the others. If you cut at 0.5, you will get an ellipse. If you stretch it, increase L, it becomes narrow. The pass band becomes narrower. If you make it thicker, it goes to the lower frequency band. If you rotate it, it rotates, that's all. So that is the effect of the design parameters. Okay. So the texture orientation was determined as the orientation of the Gabor filter that yielded the highest magnitude response. So in this case, we used 180 filters. We don't need 181 degree separation of filters. We could have done with 90 filters perhaps, but we left that optimization to later stages. We said at the beginning, let's just do 1 degree separation. So apply 180 Gabor filters at multiple scales if you want. And of all of those, what is the maximum response at this current pixel? Take that. And then what is the angle of the Gabor filter that gave you the maximum response? Keep that as the angle. So you form a magnitude response image and an angle response image for every pixel in the given image. So there is a magnitude response and the orientation field. Or the orientation field is a combination of the magnitude and angle at every pixel. So this is simply a representation. You are convolving the given image with a GK, that is the Gabor filter. The orientation is given by theta xy is alpha k max, where k max is the argument of the max of the FKXY, which are the responses of the K filters. But that's what I already said. Now, how do you characterize this with phase portraits? So let this delta xy be sin x, theta xy minus pi xy given A, B. You have found, you want to find A and B. There is an error. Sin xy minus pi xy given A, B. That is the error, and you want to minimize that and find the A and B parameters that minimize this error. There is an angle field given to you, and there is an angle field of the orientation field of the model. You start with some AB, and it will give you that phase portrait, the angles. But from the mammogram, you have computed some angles. The two must match. And this is the error if they don't match. And modify A and B until they match, and find A and B. So for that, a nonlinear least squares algorithm was used. So for a given image, you compute three maps, three phase portrait maps. But you can't do this in one shot for the whole image. A mammogram has so many details. So you put a small, what is called analysis window, over a small portion of the mammogram, and do this analysis, phase portrait, find the phase portrait for that, and keep sliding the window and analyze the phase portrait. And create a node map for the entire image. So create three maps, slide the analysis window through the orientation field of the region of interest or the entire image. At each position of the window, determine the type of the phase portrait. Is it node, saddle, or spiral, based on the eigenvalues of A. Increment the value at the location of the fixed point. Fixed point is minus A inverse B. In the corresponding phase map, node, saddle, or spiral. We don't care for spiral, we don't care for saddle, so only one node map. If you want, you can create all of the others. The size of the analysis window was set as 44 by 44 pixels. In consultation with the radiologist as to what the size should be to capture the details. Let me go to the results here. The entropy of the phase map of HXY is again HXY over S. This is just a normalization factor times log of that. A map with dense spatial concentration of votes in the node map is expected to have a large maximum value and a low entropy. On the contrary, a map with a wide scatter of votes may be expected to have a low maximum and large entropy. The question is, we got a map. Is there one strong point where I can say that is a node? Or have the votes been cast at multiple different points? It's a scatter, so there is no real node. That is what we want to distinguish here. So for that, we use the entropy. So let me show application to a part of a mammogram. This is the part of the mammogram in the MIAS database that was marked as having architectural distortion. So when you apply Gabor filters, we get this. Clearly, you can see these fibroglandular tissues going in different directions. This way, that way, and so on. And that is the focal point, the center of that window, as marked in the database. These are the angles obtained for the Gabor filters. So when you have something here, you can see the angle there. When you have something there, you can see the angle there. They align. This is the node map. Saddle, spiral, there is nothing particular. Node map, there is something here. This is where we have a focal point. This is only for that part of the image. So this design is okay, at least in this basic image. So we did some analysis and with parts of images, and I'll skip all of that and let's go to a full image. The orientation field was filtered and downsampled. So we have this flow chart here. I'll skip all of that and go to the result here. So here's the full mammogram. And this is after initial pre-processing, some smoothing. You can see the smoothing there. And C is the orientation field. This is after filtering the orientation field. The orientation field that you estimate could have noise in the sense these angles may not be properly estimated. By filtering these angles, you see better alignment. And here, you see clearly a node point, meaning you have various directional components there. Elsewhere, you see the convergence of tissues going in a neatly ordered way. Not all of them, but you don't have such a pattern anywhere else. So the node map and the filtered node map, there is one large value there, but there are so many other large values. This is also a large value. So when we filtered the node map and put additional criteria, we reduced the node map to 2 large values. The details are there. You can read later if you wish. Filtering of the node map to remove scattered points by accumulating, like a Gaussian filter. Accumulate closely positioned values and build local peaks. Scattered values are rejected in the node map. So from this, we get this. So 2 large values, peak detection becomes easy. So detect peaks in the node map, and we got 2, one there and one here. This is the area marked by the database. This is what we detected. We detected this also, but this is the nipple. And at the nipple, these structures must converge. So that is a partial node. There is nothing coming from outside, but these are all converging. So that is a point of convergence, and a node is a point of convergence or divergence, whichever way you see. Diverging, converging, we don't know if it is going this way or that way. There is no direction to 360 degrees, only 0 to 180. So this is a false positive, but it is understandable. So there is a technique known as free response receiving operating characteristics, like receiver operating characteristics or ROC analysis. But this is free response, which says, what is your sensitivity of detection of these points you want to detect in your database versus false positives? How many false positives will you put up to achieve that sensitivity? So by varying the cut point of some parameter, you can modify the sensitivity. That is, how many points can I mark on the image before I get the architectural distortion point correctly? Like throwing darts or putting pins. So I can close my eyes and put 1,000 pins per mammogram and I will get the correct answer. I'll find the point of architectural distortion, but there will be 999 false positives. That's useless. So if I put only one point, if the radiologist says, I allow you to mark only 1 point per image, then quite likely I'll miss many real points of architectural distortion. So then the question becomes, how many false positives can the radiologist tolerate and allow me to catch architectural distortion with higher and higher sensitivity? That is, how many real points of architectural distortion in the database will I detect? So if no false positive is allowed, my sensitivity is very poor. If 5 false positives are allowed per image, I get 55% sensitivity. So if I want 80% sensitivity or 90%, I have to put some 12 or 13 points per image. This is the initial stage of our research work on architectural distortion by Fabio Iris, which was 22 years ago, 2003 if I remember, 2004. Later on, Shantanu Bonik did some work on this and we got better results. I'll show you that in my seminar, perhaps on the last day. But this is how research work starts. At the beginning, you need to understand what the problem is and propose some methods. You may not get the best results, but still there is something worthwhile. There is a reasonable methodology. It is giving some results that are reasonable. There are limitations, yes, everything has limitations. But there is something interesting. Perhaps the idea is, pull this here, you want to go straight up and across. Or you want to go straight up 100% and no false positives. That is ideal. So you want this curve to go shoot as straight as possible like that and stay at the top. So that is the goal. And we haven't reached that, but as I'll show you later on in Shantanu's work, we have come closer here. So that's the end of this chapter. We have seen that preferred orientation and directional distributions relate to the functional integrity of several types of tissues and organs. And changes in such patterns could indicate structural damage as well as recovery in the case of ligaments. Directional analysis could be used to study the health and well-being of a tissue or organ, as well as to follow the pathological and physiological processes related to injury, treatment, and healing. In the case of mammograms, it could assist in the detection of asymmetry and architectural distortion, two signs of breast cancer, two manifestations of breast cancer that were initially ignored in the early research on detection of breast cancer using mammograms. So that concludes the textbook material. I have gone fast, so we have more time to discuss or present some new results based on our research projects next week. And we will also have a few other lectures. Dr. Narasimha Dan is not here, but he is going to give a talk after our tea break now. And Dr. Shyam, what's his last name?
Shyam.
Dr. Shyam Lal will give a few lectures next week. 3 lectures?
The next week.
And how about you?
The next week.
Next week. Dr. Raghavendra also will give some lectures next week. I have indicated in the original plan that I'll give 3 seminars related to our research, totaling about 5 hours. But I think I'll take more and I'll add 1 or 2 more seminars. I may take 7, 8, 9 hours next week. And then I didn't know I would be finishing this today, but as you saw, I skipped some minor details. You don't need to know all the parameters of these equations that were used by my students then. Those are not important. The main idea is important. What was the methodology and what was the way of thinking in designing those methods? That should be enough. If you want minor details, they are there in the notes. If you want more details, go to the papers or the book. Or write to me, I can send you the papers. I can't send you the book because the copyright is with the publisher, but I can send you our research papers. Or you can find them. All libraries have access to IEEE and so on. Are there any questions? Before our tea break, we have 3-4 minutes for some discussion. And then I'll be off. I'll see you on Monday. Questions? Comments? Good, bad, whatever. Feel free to express whatever you have to say. Nothing? Okay, we'll have a tea break. Thank you.
Okay, we'll have tea break from half an hour. So, just speak in.
Hi, good evening everybody.
Good evening.
Works.
Works.
Still we have 4 minutes.
Yeah, still have, yeah. Okay.
Before starting this session, I want to ask what type of math background you have, that you know linear algebra, stuff like that, matrix theory part. What is that you don't know so that we try to cover more in the next week? So What do you want to know?
No, sir.
Huh?
A little of linear algebra, but not into depth.
Oh. Very fast. You want some advanced linear algebra?
Yeah.
How about probability random process? You want it to be advanced linear algebra? Okay. Okay. Okay, I wanted to know what math background you have, what you are comfortable with. So next week probably Professor Rangaraj will cover more on his research and more applications. So we have seen a lot of theory here. So, and organize some more guest lectures from our faculty. They'll talk more on deep learning aspects probably. One on computing.
Yeah, sir. You could use what level?
We just want to see some results like
Yeah.
like we don't want total of coding and all, but we just want to see some results where it is being used currently. That
Let's see. Initially that was not our plan.
this is a suggestion.
Like some problem statement which the vector can continue.
Okay.
Practical applications where all these steps that are covered here and here, if you could show us. That's
Here's
better.
code application also. Theory followed by show the result.
Show it here, like, there and when we are given that links also, it is only report.
That's one of the textbook patterns there. But anyway,
I was suggesting a session particularly on the basic advancements in recent days in the problem statements and also discussion on some resources for all it's actually because all are pros here.
all are
Pros here and we are like competing.
you want like more of data sets,
Yeah,
links,
at least
resources.
one session on what we can further research on few.
Okay, please. Okay, we'll start the session.
Yeah.
Okay, so welcome back. This lecture will be handled by Dr. Narasimhan. Just introducing Narasimhan in the faculty in the C department. He received his BE in Electronics and Communication from Andhra University, MPhD in Signal Processing from University of Technology, Guwahati, and PhD from Electrical Engineering, University of Science, Bangalore. Since 2014, you are a faculty here.
13,
He's, associate professor. He was mine contemporary in University of Science as well as here. So his research interest is in medical imaging, medical image processing, and computer vision, deep learning, and pattern recognition. So I request Narasimhan to take over.
Thank you, Raghavendra, for a brief introduction of mine. So today we will have a basic or introduction to the pattern recognition, a basic class for the pattern recognition. So you have been working with the deep learning for some time back. Okay. Have you ever thought about the basic building block for the neural network? So today what we are going to do is that we are going to look at the basic building block for the neural network. So that is the design of a two class classifier or two class linear classifier. Using least square method. So we are going to see this topic, and this is the basic building block for the nonlinear classifier, such as the neural network and deep learning, deep networks. So what I do is that I just take the example and illustrate how you can design the two class linear classifier, using that data. So the data we take, for simplicity, what we do, we take a simple data that you know. So we take, in the example, we take 3 images. What are the 3 images? The data, the 3 images that we are going to take. Out of 3, we see 2 images, right? 2 images belong to the benign class. You say benign class. Let's say it belongs to class 1. Let's say you have 3 medical images. Out of 3 medical images, you have two images which belong to the benign class, and the 1 image belongs to malignant. Let's say that this is a class 2. And we already studied about the feature extractions. We have studied about how you can take the GLCM features, right, from the images. What are the GLCM? The gray level co-occurrence matrix features. What those include? Those features include energy, autocorrelation, and many more features, right? So let us consider only one single feature. Let us say we are considering only the energy feature. From the GLCM features. We are only considering a single feature. We are not going to consider other features. Only we are going to consider a single feature. Let's say we are extracting the features. There will be an extractor to extract the energy feature. So we extract the feature from the given images. Let's say the energy of the 2 benign images are let's say the first image feature is, let's say for the first image we have the 1 unit. Let's say, when we don't get into actual the what do you call, right? So we don't look into the the specific measurement of this, but you would say that the energy of the image is 1 unit. Okay, first image energy is 1 unit. Okay, the second image, the 2 unit. Now the third image, let's say the third image, the feature is, the energy of the third image is 3 units. Okay, we have extracted the features. Now, this feature, the first image feature belong to this feature, the first feature that you see here, right? This one feature value belongs to which class? Class 1. And the second image, right? The second, the 2 value here, the 2 feature value belongs to, again, the class 1. Let's say the class 1 is labeled as 1. Okay. Then we have another feature, the 3, which belongs to, let's say, the class 2. The class 2 labeling is a -1. And these are the feature values. The feature values, and these are the labels. Now we got the features from the images that we have taken. What are these images? These are the images, 3 images. Out of 3, 2 are from the benign class and 1 from the malignant class. Let us depict these feature values in the feature space. We have something called feature space. How many features we are taking here? We are taking only a single feature. Now the feature space is a one-dimensional space. Since we are taking one feature, your feature space is a one-dimensional feature space. So let us depict these points on the feature space. Let's say this is the variable, the feature variable, which takes the energy of the images. Now, at x equal to 1, what is that we have? What is, when I say x equal to 1, this feature value belongs to the class 1. Let's say the class 1, right, is represented like this. Now, x equal to 2, when I say x equal to 2, x equal to 2, right, value, feature value, this belongs to which class? Class 1. Let's say the class 1 is represented like this. Now the third feature, what is the third feature value? 3, right? 3 belongs to class 2. Let's say this is this, right? So in the feature space, the distribution of the features like this. What we have shown here is the distribution of the feature values. How many values we have? Right? We have 3 feature values here, and we have depicted. Okay, we have put these feature values in the feature space. Now we define a classifier now. By looking at this, the feature space, Now we can define a classifier. I can define the classifier like this. Now my classifier is this. What is my classifier is? My classifier is h of x. H of x takes, h of x gives you a 1, right? It will give you a 1. 1 represents the class 1. If what, right? If it is equivalent to 1, if, can I say this? If x less than 2.5.
Why can't we take 3? Less than 3 also is class 1.
Yeah, you can take any point. See, by looking at the feature space, you can take this point to classify to separate the two classes. These two feature values belongs to class 1, and this one belongs to class 2. I can put a threshold. I can put threshold here, or here. I can take any threshold and I can define the classifier. I can define the classifier like this. The h of x is equal to 1 if x less than 2.5. You can take, this is called the threshold. Okay. You can take any threshold between this. Now, it is equivalent to -1 otherwise. Now, if the test data comes, now we have not used any processor to design this. What we have done here is that we have looked at the feature space and we have defined the two-class classifier. We have defined the two-class. We have not used any procedure, to find the threshold. By looking at the feature space, right? We have come up with a two-class classifier. Now, if the test data comes, let's say you are given an image, unknown image. It may be a benign, or it may be the malignant. Now, given an image, right? Let's say you are given an image. The first thing what we need to do to use this, we need to extract the feature, right? What is the feature value? Maybe it can be anything. Let's say it is equivalent to 4. Now what the classifier says? By looking at these feature values, we already defined a classifier based on the feature space. Based on the data available to us, we have defined the classifier. We have defined the classified based on the data that are with us. Okay, so this data is called the training data. For your information, this data is called whatever the data we have here to train, right? This is called the training data. Now, by looking at the training data, we have defined the classifier here. Now it's a time to test the classifier. Whether classifies correctly or not. It may misclassify, it may classifies correctly. Right? So how do you check? We need to keep, right, some of the data as a test data, which has the labels. Okay, right? Let's say this, you are given unknown image. We don't know the label. Now we ask, the classifier to take the decision. We give this image. First, we give it to the feature extractor. The feature extractor will extract the feature, and the feature value given to the classifier. What the classifier says is that, right? If this is the feature value, the classifier says that this image belongs to this image belongs to H of 4 belongs to what? Plus this belongs to class 2. Yeah, it gives you minus 1. Minus 1. It gives you minus 1. So practically what you do, you keep some data for the validation. Before you test the classifier with the unknown data, what you have to do, you have to keep some data, some part of the training data for the validation. Okay, right? In general, I can define the classifier like this. In general, h of x is equivalent to 1 if a1x plus a0 is greater than 0 and h of x is minus 1 otherwise. In general, why I am saying in general? The function that you see here is just x. What kind of function is this? The threshold that we have kept here is the 2.5. In general, since we are into one-dimensional, right? We are looking at the one-dimensional feature. So in general, the function that you see here can be something like this. And the threshold, right, without loss of generality, you just keep the threshold is 0. So this is the definition that you see for the 2-class linear classifier for one-dimensional space. One-dimensional for 1D you say, right? 1D. And this function that you see here is called the discriminant function. This function is called what is this called? This is called the discriminant function. Why we call this as a discriminant function? It discriminates the 2 classes. It discriminates this function, say like, right? This function is called the f of x is called the linear discriminant function. Linear discriminant function. What if, suppose let's say you have n feature values. If I have n feature variables, how you define the classifier, 2-class classifier? How you define that? In general, for n-dimensional case, for the n-dimensional case, you define the classifier like this. How you define is, let's say you have n feature variables, x1 to xn are the feature variables. Is equivalent to 1 if what? If what? In the general case? In the general case, an xn plus an minus 1 xn minus 1 plus, yeah, right? So you have the a0 is, and this is equivalent to minus 1 otherwise. otherwise. Can you put that in vector form? Can we put that in vector form? I can put that in the vector form. How do I put? I can define, this is a definition. I can define the two-class linear classifier as h of x. The x is a vector whose elements are x1 to xn. Is equivalent to 1 if W transpose x plus a naught is greater than 0 and the classifier is -1 otherwise. Where W is, what is this W? What is this W? Yes. So this is you can say A1, A2 to AN. A2 to AN. Right? Is that correct? X1 W transpose is that. So this one, right? So what is the W transpose X now? If you know, you can define like this. W transpose is that, right? Transpose of this vector, and X is the, where X is, what is X here? What is X? X1, X2, is that right? But you have to look at it, you have to satisfy, we are saying this, right? So we have to, when you take the dot product between this and this, you should come like this, okay? Right? So is this correct? So this is actually the definition of the two-class linear classifier, and this is the building block for the non-linear classifiers. This is the linear classifier, and this is the building block for the non-linear classifier. And in the literature, what is this called? This is called this is linear classifier. A special case of this is called the perceptron. We know that the perceptron is the building block for the neural network, building block for the CNNs. So you can use the CNN as a nonlinear classifier. Now let us look at, we have started with the example, but we have different, somehow, we have got the classifier, but this classifier we have not derived using any of the method. What we have done here is that we just have looked at the feature space and we have defined like this. Now, is there any method, any formal method with which you can get the two-class classifier? What do you mean by getting a two-class classifier? For the given data, what is that we have to do? For the given data, we need to train the classifier, right? What do you mean by training the classifier? For the given data, the training means getting the parameters of the function. This is my function. It's a function of W, X. X is the input that you give, and W, which characterizes the linear function here. And finding a linear classifier for the given data is nothing but getting the parameters for the parameters which characterize the linear function. Right? Now we have this data. Now can we get the parameters A1, A0? Why we are taking this? Because the data that we have considered here is of one-dimensional data. So if it is one-dimensional data, what is the linear classifier? This linear classifier, this is a general linear classifier for the n-dimensional. For the one dimension, the linear classifier is this. Using this training data, we need to get these parameters. Using this data, we need to train the classifier. The training of the classifier means getting these parameters. There are many ways to get these parameters. But one of the method you can use is the least square method. Can we apply least square method to get these parameters? Yeah, we'll apply least square methods to get these parameters. We already have some kind of classifier here. But what we have done to get this classifier, we have looked at the feature space and we had defined this. We have defined something like this. We have taken the threshold, right? If x is less than 2.5, then we say that this is the feature value belongs to class 1. But now if I use the least square method, what is the change in the two class classifier that we get? The change is this threshold value will be changed. The threshold value will be changed. You see that we use the least square method, and you see that the threshold that we are going to get is a different one. Here, we just looked at the feature space and we have defined this. We have set up the threshold, right, and we have defined the two class classifier. But if you apply actual method, if you apply least square method, what is the threshold that it would give? Can we go ahead? Can we see there? Can we apply the least square method? How many of you know least square method here? How many of you know least square method? Okay. So you don't require linear algebra. You can, if you know linear algebra, it is very easy to understand. But okay, if you don't have a linear algebra background, no problem. I'll try to make you understand. Okay, with the simple mathematics. It's easy. It's not difficult you to understand this. So we have defined the classifier, two class classifier like this. Here, this function is a linear function, and we have put threshold here. If I substitute x equal to 1, ideally what is that you need to get here? We need to get a positive value. Ideally we need to get, if I substitute x equal to 1 here, what is that I have to get? I have to get 1. If I substitute 3 in this, what should I get? I should get, this must be negative value. Okay. So, ideally, right, since we are keeping threshold here and, we expect this, this function to give a -1. Okay. So, when I substitute x equal to 1, what should I get? When I substitute x equal to 1 in this function, what should I get? 1, right? 1 I should get. If I don't get 1, what is that? There would be error. Okay. So the error is this. This would give you, this supposed to get, if it is 1, then 1 minus 1 is 0, right? There is no error. But we don't know that this would give you 1 value. There would be error. This is the function, my function. I substitute value. There is no guarantee. It need not that, it would give you 1 value here. If it doesn't give 1 value here, then there will be a error, right? So the error is this. Now generally what they do, they'll take like this error. No, right? So what they take is square. Okay. No, this is the error for x equivalent to 1. What if x equivalent to 2? What is the error? This minus 1. Okay. If I substitute x equivalent to 3, what should I get? I should get the minus 1. If I don't get minus 1, there would be an error, right? So the error is we have 3 errors. Then what do? We add up. Okay, you add up. Then what we have to look for? There is error, right? So it's called the error function. Let's say this is called the error function, right? So you can say this is the, what is W here? What is X here? Okay, let's say this is the error function, right? We got the error function. Now we have to minimize this error function with respect to what? We have to minimize this function with respect to A1, A0. These are the parameters which characterize the linear function. The error must be minimum with respect to this. This is my error. What you are looking for is the minimum of the sum of the squares with respect to A1 comma A0. You are looking at the least of the squares, sum of the squares. So it's called the least square. It's called the least square. So you are looking at the if I say this problem is called the least square problem, right? So you try to minimize with respect to A1, A0. That would give you the parameters that would give you the minimum of this, right, are called the least square method parameters. Now how do we minimize this? We don't require high-fi mathematics. We don't need to do. Have you done optimization course? No, but optimization course. Okay, no problem, right? If you have not done, no problem. You can easily understand. So how do you minimize this? How do you minimize this function? This is a function of 2 variables. How do you do that? When you have the function which is a function of the two variables, what we do? We already seen this in the minimization of this in 11th and 12th, right? So somewhere we have seen this, right? What do you do actually? We take the partial with respect to the partial of j with respect to a1, right? And the partial of j with respect to a0, and then equate to 0. What is that we have taken here? We have taken the gradient of this function, and we have equated to 0. So we have taken, we have to take the partial of this with respect to a1 and equate to 0, and take the partial of j with respect to a0 and equate to 0, and solve we get, when I do this, I get a linear equation. If I do this, again I would get another linear equation. Can you work out this? Anyway, I have results. Okay, you don't need to do that. I have so you can try at home, but I will give you straight away the results. Okay, at least I'll give you the linear equations. Okay, so why do you get the linear equations here? Why do you get linear equations? Because the equation that you see is a quadratic equation. If I take the derivative of that, what is that you get? Linear equation. So two linear equations you get. So you will have the two set of equations, right? Now you solve those two equations. I'll give you straight away what are those equations. So what are those equations? Equations are this. One is 28a1 plus 12a0 is equal to 0, and then the other equation is 24a1 plus, other equation is, probably you would get something like this, 12a1 plus 6a0 is equal to 2. So you get a two set of linear equations. One is this, second one. Now can you solve this? What do you get? You know, right? How do you know how to solve the two set of equations, linear set of equations? Right? It's easy, right? We don't have any problem. So what is that? What are the a1 and a2? A1 is equal to, I'll give you straight away, okay, minus 1, and a0 is 7 by 3. Okay. So these are the parameters that we got for the linear equation, linear function. Okay. Now you define, I will define, right? We already defined what is a linear classifier. The linear classifier, we defined something like this. Sorry. This is equal to 1 if a1x plus a0 is greater than 0, and this is equal to minus 1 if otherwise. Now you look at, you substitute the values a1, a0 in this, and what you get is h of x is equivalent to 1 if minus x plus 7 by 3 greater than 0, and this is minus 1 otherwise. Okay. Right? Now we just have to do some manipulations here. Okay. Then you can define h of x is equivalent to 1 if x, can you tell me x from that, x less than 7 by 3, right? Is that correct? Is equal to minus 1 otherwise, right? Sorry, otherwise. Now by using the least square method, we have got the classifier is like this. But can you compare this with the previous classifier that we have got by looking at the feature space? Can you compare this classifier with the classifier that we got just by seeing the feature space? I'll just erase this, okay? Now we have a feature space, something like this. We have a feature space something like this, and by looking at the feature space we got the h of x as h of x is equal to 1 if x is less than 2.5, otherwise, right, minus 1, otherwise this. You see that the difference? By looking at the feature space we got this, but now you see that, but what is the difference here? What is the difference between this classifier and that classifier? Both are, both gives you the, correct classification. But what is the difference between this and this? Here there would be change in the threshold. Yeah, yes, right. So there will be change in the threshold value. So we have put somewhere here threshold. But least square method gave us a different threshold. A different approach would give you a different threshold. If I use perceptron algorithm, there's something called perceptron algorithm. If I use the perceptron algorithm to train your linear classifier, your threshold would be something different. Both classifier classifies the training data correctly. What is the training data here? The training data is this, right? Can you see, both classifier classifies correctly the training data? If I substitute, right, this is my training data. Substitute x equal to 1. What the two classifier says? This is the one classifier, this is the other classifier. Both classifiers would say the given feature value belongs to class 1. And if x equal to 2, both classifier says class 1. 3, both classifier says this feature value belongs to class 2. and this is the building block. Now what I do is that I define a classifier something like this. What I do is that I say I just apply a sigmoid function. Right, to the linear function, the sigmoid of or for the 1D case right. Okay. You know very well about the sigmoid function. How many of you know about the sigmoid function here? What this gives you? If I plot the sigmoid function versus this function, okay? The sigmoid of how this would be, how the sigmoid function would be. What is this sigmoid function? This is this sigmoid function is equal to 1 by 1 plus e power minus this a1 x plus a naught. Sorry, we have to do this. Okay, this is my sigmoid function. When this function value is 0, what is the value of the sigmoid function? What is sigmoid function value? If it is 0, if this is 0, what is the sigmoid function value? This one, right? Which is equivalent to, let's say, this one is 1 minus, maybe right? So 1 by 1 plus e power minus a1 x plus. Now, if this is 0, what will happen? This would be 1. 1 by 1 plus 1. How much? Huh? 0.5. Okay, 0.5. Now, if this is infinite, what is that? If this is infinite value, what is that it would give you? If this is infinite, e power minus infinity is a 0, and what would you get is, you would get a 1 value. So at infinity, 1 value, at minus infinity, what is that you get? You're saying 0, right? So how the function values, if I plot, if I depict all the function values, how the graph would be? The graph would be something like this. Right, so it's like it tends to 1. Okay, it goes to 0, and it eventually gives you the value of 1. Okay. Why do you want to do this? Why we compress? See, what we are doing is that we are compressing the values, the value of the linear function. We are compressing the values to 0 and 1. Now I define a classifier differently. Right? What is that I do is that h of x is equivalent to the classifier takes class 1, okay, the class 1 is represented by 1. If the sigmoid of this is greater than 0.5. Now what is the threshold? See, we need to keep the threshold by looking at the function, the values of the sigmoid function. Now it is, what is the range of these values? 0 to 1. Where do you keep the threshold? At 0.5. So what you say that the classifier takes, right, 1 if the sigmoid, right, of this is greater than 0.5, and this is a minus 1 otherwise. So sigmoid function more of gives you the probabilities. It gives you the values in between 0 and 1. Right, the probability values always in between 0 and 1. So it would give you the probabilities. Now you are looking at the probabilities and taking the decision. You are looking at the probabilities here. For the given feature, I substitute here. I know how to get A1 and A0. I substitute for the given x, I get this function value. If this function value is greater than 5, what I would say is that I would say the x belongs to 1. The x belongs to class 1. What does that mean? If for the given feature value, if the probability is high, what the classifier says? The classifier says that the x belongs to class 1. If the probability, if this value is less than 5, means that if the probability is low, then the classifier says that the feature value belongs to class 2. Now the interconnection of these classifiers would give you what? If you connect in a specific way, what you would get? If the interconnection of these two classifiers would give you, there is a linear classifier. Still, it is a linear classifier because it can gives it it separates the classes linearly. Though you applied sigmoid function. Sigmoid function is used to convert the values into probabilities, right? But this sigmoid function plays a key role in getting in neural networks. Already told you that the building blocks for the nonlinear classifier, right, are the linear classifiers. You interconnect the linear classifiers with this function, You apply the sigmoid function at the output of each and every linear classifier, and you connect these linear classifiers together. Then the whole network, the whole classifier acts as a nonlinear classifier. At the whole network, or you would say that the whole network is considered as the neural network. We'll stop here. I don't want to get into if time permits, we'll again meet. I am going to teach you convolutional neural networks, and then if I get chance, if Raghavendra gives me time, then I will talk about the GANs, PCAs, autoencoders. So many more I talk about. Now, if you have any doubts, can ask. Do you have any doubts on this?
Suggestion,
See, if you want to understand, take a simple problem and try to design. Okay, so like what we have done here, we have taken simple data and I have designed the classifier. Say, take a simple, always simple, look at simple data and then you try to design. Then you will understand many things. And what we do is that generally we don't understand the basics, then we look at the hi-fi things. So what I say is that understand what are the building blocks. These are the building blocks. If you understand these things completely, then you will understand the bigger things. So you always try to understand everything in terms of mathematics. If you have a good mathematical background, you will understand many things. Try to understand everything in terms of mathematics. Okay, thank you.